Hello there, and welcome to Science for Sleep, where curiosity slows its pace and the universe becomes a quiet place to rest your thoughts for a while. Wherever you are right now, whether you're settling in at the end of a long day or drifting gently towards sleep, I'm glad you're here. Tonight we're going to explore something vast, something familiar, and something surprisingly personal all at the same time. We're going to talk about our cosmic neighborhood, not the entire universe, not the edge of existence, but something much closer to home. The place where our galaxy lives, the local group. Now, when people hear words like galaxy group, they often imagine something tidy and well-defined, maybe a neat cluster of glowing spirals arranged like ornaments on a shelf. But the reality is softer, looser, and far more expansive than it sounds. The local group is not a sharply bordered region. It doesn't have a fence around it or a sign saying you've arrived. Instead, it's more like a quiet island in a dark ocean, held together by gravity drifting through space, surrounded by emptiness that stretches farther than the mind can comfortably picture. So tonight, we'll take our time and gently ask a simple question that turns out to be anything but small. How big is the local group really? Not just in numbers or units, but in presence, in distance, in meaning, in how it fits into the story of where we are. Before we go any further, let me ask you something simple. Where are you listening from tonight? Are you somewhere familiar and comfortable, or somewhere new? And what time is it where you are right now? It's a fitting question, considering that everything we'll talk about exists on timescales so long that clocks almost feel like a joke. Still, here we are, measuring moments, breathing slowly, letting this one stretch out gently. If you find this kind of quiet exploration soothing, or if it helps your thoughts slow down after a busy day, you're very welcome to like the video or subscribe. It helps this calm little corner reach others who might need something steady and unrushed before sleep. And if you don't, that's perfectly fine too. You can just rest here for a while. Now, let's ease into our topic without rushing it. When we talk about the universe, we often jump straight to the biggest ideas. Billions of galaxies, trillions of stars, distances so large they lose meaning almost as soon as they're spoken. But our story tonight begins closer than that, much closer. It begins with a small collection of galaxies bound together by gravity, moving through space as a kind of family. This family is called the local group, and it includes the galaxy you live in, even if you've never thought about it this way before. The local group is not a single object. It's not a structure you could fly around in a neat circle. It's a loose gathering of more than 50 galaxies, maybe more depending on how faint and hard to detect you're willing to go. Some are large and bright, filled with hundreds of billions of stars. Others are small and dim, barely visible even with powerful telescopes made up of only a few million stars scattered thinly through space. All of them, though, share something important. They are close enough, cosmically speaking, to feel each other's gravitational pull. Gravity is the quiet organizer here. It doesn't announce itself, it doesn't shine, but it decides who belongs together and who drifts away. The galaxies of the local group are not flying apart with the expansion of the universe, at least not from one another. They're moving together, bound into a shared region of space, like leaves swirling slowly within the same eddy of a vast cosmic river. If you were able to step far enough back, far beyond our galaxy, far beyond even our nearest neighbours, the local group would look like a faint, irregular cloud of light spread across millions of light years. No sharp edge, no obvious centre, just a loose gathering of stars and dark matter drifting through the dark. That raises an interesting thought. When we ask how big the local group is, what are we really asking? Are we asking about the distance from one galaxy to another? The span of gravity that holds them together? The region of space where the local group's influence still matters? Each of these gives a slightly different answer, and none of them are wrong. To begin understanding the scale, it helps to start with what we know best, the Milky Way. This is our home galaxy, a sprawling spiral of stars, gas, dust and dark matter about 100,000 light-years across. That alone is already a size that's difficult to imagine. Light, moving at the fastest speed anything can travel, takes 100,000 years just to cross it. Every star you've ever seen in the night sky belongs to this one galaxy, along with hundreds of billions of others you've never seen. But the Milky Way is only one member of the local group. It doesn't sit at the edge, and it doesn't sit exactly at the centre either. It shares this region with another giant spiral galaxy called Andromeda, which is slightly larger and more massive than our own. Andromeda lies about 2.5 million light-years away, which means the light reaching us from it tonight began its journey long before humans were around to watch it. Between the Milky Way and Andromeda, gravity is already quietly at work. These two galaxies are moving toward each other, slowly, steadily, at a speed of about 100 kilometers per second. That sounds fast, but on cosmic scales it's almost gentle. Their eventual meeting is billions of years away, so distant in the future that the continents of Earth will have shifted, the sun will have changed, and humanity as we know it may be long gone. Andromeda is not alone either. There's a third large spiral galaxy called Triangulum, smaller than the other two but still substantial. It floats nearby, caught in the same gravitational web, moving along with them through space. Around these large galaxies orbit dozens of smaller ones, often called dwarf galaxies. Some are stretched and distorted by gravity, slowly being pulled apart. Others glide quietly, barely interacting at all. This is where the local group begins to feel less like a simple list and more like a living system. Galaxies orbit galaxies. Some merge. Some are torn into streams of stars. Some fade almost entirely into darkness, leaving behind only a faint gravitational signature. Over billions of years, this quiet motion reshapes the group again and again. So how far does it all extend? If you measure the distance from one end of the local group to the other, taking into account the most distant member galaxies still gravitationally bound, the answer comes out to roughly 10 million light-years across. That means light would take 10 million years to cross the entire region. Even that number, though, is a little fuzzy, because the boundaries of the local group are not fixed. They blur into the surrounding universe, where other galaxy groups begin to dominate. 10 million light-years is an enormous distance. If the Milky Way were the size of a coin, the local group would be larger than a small city. And beyond it, the universe continues, filled with countless other groups and clusters, each with their own internal gravity, their own slow dances through space. What makes the local group special isn't just its size, but its isolation. Compared to massive galaxy clusters containing thousands of galaxies packed tightly together, the local group is relatively sparse. Its members are spread out, drifting through large volumes of dark space. This quiet arrangement has shaped the history of the galaxies within it, including our own. Because we're not in a crowded cluster, the Milky Way hasn't been violently disturbed as often. Its spiral structure has remained intact for billions of years. Star formation has proceeded at a steady pace. The environment has been calm enough for complex structures to form, including planets, and eventually life capable of wondering about its surroundings. That thought can be grounding. When we talk about cosmic scales, it's easy to feel small in a way that's unsettling. But there's another way to look at it. We exist in a region of space that is large enough to be stable, quiet enough to endure, and rich enough to give rise to awareness. The local group is not just a measurement, it's a setting. You're not just on a planet orbiting a star inside a galaxy. You're part of a quiet gathering of galaxies, drifting together through an enormous universe. The local group is vast, but it's also familiar in a way. It's home territory on the grandest scale we can reasonably claim. Take a slow breath here. There's no rush to move forward. The distances aren't going anywhere, and neither is the story. We'll keep drifting gently, step by step, into a clearer sense of just how large this cosmic neighborhood really is. To understand what the local group actually is, It helps to first loosen the way we usually imagine space. We tend to picture it as neatly divided, like countries on a map or rooms in a building, each with clear borders and names. But space does not work that way. It is not parcelled out with lines or labels. Instead, it is shaped by influence, especially by gravity, which quietly decides what belongs together and what does not. The local group is not a solid object, and it is not a formal structure with edges you could point to. It is a gravitational relationship. It is a region of space where a collection of galaxies are close enough and massive enough that they are bound to one another. They move through space together, responding to the same gravitational pull, rather than being carried away by the general expansion of the universe. That distinction matters. On the larger scales, the universe is expanding. Galaxies that are far apart are drifting away from each other as space itself stretches. But gravity can resist that expansion locally. Where there is enough mass concentrated in one region, gravity slows the outward drift and can even reverse it. The local group exists because its combined mass is strong enough to keep its galaxies from being pulled apart by cosmic expansion. So when astronomers say local group, they are really describing a shared gravitational neighbourhood, a region where galaxies are not simply passing by one another, but are engaged in a long, slow interaction that will last for billions of years. The word local is doing a lot of work here. In everyday life, local means nearby, familiar, close enough to matter personally. In cosmic terms, local still means enormous. The local group spans millions of light years. Light itself, the fastest thing in the universe, would take millions of years to cross it, and yet, compared to the vast web of galaxies stretching across the observable universe, this region truly is close to home. The local group is dominated by two large galaxies. One of them is the Milky Way, the galaxy that contains our solar system, our planet, and every human story ever told. The other is Andromeda, a slightly larger spiral galaxy that serves as our nearest galactic heavyweight neighbour. These two galaxies contain the majority of the mass in the local group, and their gravity largely defines its structure. Because of this, the local group does not have a single central point. Instead, it has two major centres of influence. The Milky Way and Andromeda each have their own retinue of smaller galaxies orbiting them, like quiet companions moving through wide, invisible paths. Some of these smaller galaxies are clearly associated with one or the other. Others drift in between, influenced by both, belonging to the group as a whole rather than to one dominant galaxy. This arrangement already tells us something important. The local group is not symmetrical. It is not evenly distributed. It is lumpy, uneven, and shaped by history. Galaxies have fallen in over time. Some have been captured, others have been stretched and distorted by repeated gravitational encounters. What we see today is the result of billions of years of slow-motion interaction. The local group includes more than 50 known galaxies, though the exact number depends on how faint a galaxy must be to count. Many of these members are dwarf galaxies, which are much smaller and dimmer than the Milky Way or Andromeda. Some contain only a few million stars. Others are even more subtle, barely visible against the background of space, detectable mainly because of how they affect the motion of nearby stars. These dwarf galaxies are not just background decoration. They are key to understanding what the local group really is. They act as tracers of gravity, revealing where mass is concentrated and how it is distributed. Their motions tell astronomers which galaxies are bound to the group and which are merely passing by. Some dwarf galaxies orbit the Milky Way in long, looping paths. Others orbit Andromeda. A few appear to be free-floating within the group, not clearly tied to either giant. Over time, many of these smaller galaxies will be absorbed by larger ones, their stars stretched into long streams that wrap around their host galaxies like faint ribbons. This process is not violent in the way explosions are violent. It is slow and patient. A dwarf galaxy can take billions of years to fully merge with a larger one. During that time, its stars continue to shine, its structure gradually loosening until it becomes part of something bigger. The local group is shaped by these mergers, past and future alike. One of the most important things to understand is that the local group is defined by motion, not by appearance. A galaxy belongs to the local group if it is gravitationally bound, meaning it does not have enough speed to escape the group's combined gravity. Astronomers determine this by measuring how fast a galaxy is moving and in which direction. If it is moving too quickly away from the group, it is not considered a member, even if it appears nearby in the sky. This leads to a subtle but important point. Distance alone does not determine membership. A galaxy can be relatively close, but moving away fast enough that it is not bound. Another can be farther away but moving slowly enough to remain part of the group. The local group is therefore not a simple bubble of space, but a dynamic system defined by gravitational balance. To understand this better, imagine throwing a stone upward on Earth. If you throw it gently, it rises, slows, and falls back. If you throw it fast enough, it escapes Earth's gravity entirely. Galaxies behave in a similar way. Those within the local group are like stones that were thrown, but not quite hard enough to escape. They rise, drift, and loop back, remaining tied to the group over cosmic time. This also means that the local group has a kind of boundary, often called the zero-velocity surface. This is the distance at which the outward expansion of the universe is exactly balanced by the inward pull of the group's gravity. Inside this boundary, galaxies are gravitationally bound. Outside it, galaxies drift away with the expanding universe. This boundary is not sharp or visible, but it is a useful concept for understanding the group's true extent. Estimates place this boundary at roughly 3 to 4 million light-years from the group's centre of mass. That means the region of gravitational influence is enormous, far larger than the visible spread of the brightest galaxies alone. Much of the local group's true size is defined by invisible matter and subtle motion rather than by shining stars. That invisible matter plays a crucial role. Most of the mass in the local group is not in stars or gas, but in dark matter. Dark matter does not emit light, absorb it, or reflect it. We cannot see it directly, but its gravitational influence is unmistakable. Without dark matter, the local group would not exist in its current form. The galaxies would not be bound strongly enough to remain together. Each galaxy in the local group is embedded in its own halo of dark matter. These halos overlap and interact, creating a larger shared gravitational environment. It is this environment that defines the local group more than anything else. The stars we see are like glowing flecks carried along by a much larger invisible structure. When astronomers model the local group, they often focus on this hidden framework. By studying the motion of galaxies and the way they respond to gravity, they can infer how much dark matter must be present and how it is distributed. These models show that the local group is far more massive than the visible galaxies alone would suggest. Another important feature of the local group is its relative isolation. It is not part of a dense galaxy cluster. Instead, it sits in a quieter region of space, connected to larger structures by long, tenuous filaments of matter. This isolation has allowed its galaxies to evolve in a more gentle environment, with fewer high-speed collisions and less extreme gravitational disruption. This quieter setting may have been important for the development of complex structures within the Milky Way, including stable planetary systems. In denser clusters, galaxies experience frequent close encounters that can strip gas and disrupt star formation. The local group's calmer history has allowed its largest galaxies to maintain their disks and continue forming stars over billions of years. The local group is also moving. It is not stationary relative to the rest of the universe. As a whole, it is drifting toward a much larger concentration of galaxies in a nearby region of space. At the same time, it participates in the general expansion of the universe on larger scales. These motions are layered, overlapping, and not always intuitive. Despite this complexity, the local group remains a coherent structure. its galaxies share a common gravitational fate. Over time, they will continue to interact, merge, and reshape one another. The Milky Way and Andromeda are on a slow collision course that will eventually transform both galaxies into something new. Smaller galaxies will be absorbed. The group will become more compact, not more spread out. This future tells us something important about what the local group really is. It is not just a snapshot of the universe as it happens to look right now. It is a long story in progress, a slow narrative written in gravity, unfolding over billions of years. When we talk about the local group, we are talking about a system with a past, a present, and a future. So what exactly is the local group? It is a family of galaxies bound together by gravity, shaped by dark matter, defined by motion rather than appearance, and evolving slowly through cosmic time. It is large beyond everyday comprehension, yet small compared to the grandest structures in the universe. It is where our galaxy belongs, not by chance, but by the quiet rules that govern how matter gathers and stays together. When we talk about the local group, it's almost impossible not to begin with the place we know best, even if we rarely think about it in these terms. The Milky Way is not just a backdrop to our night sky. It is not merely a band of light stretching faintly overhead on clear evenings. It is a vast, structured system of stars, gas, dust, and dark matter, and it plays a central role in defining what the local group is and how large it feels. From where you are sitting right now, the Milky Way does not feel large. The ground beneath you feels solid and immediate. The room around you has edges, but the galaxy you inhabit extends far beyond anything your senses can register. Every star you have ever seen with your unaided eyes belongs to this one system. Every constellation is simply a small pattern traced within a much larger arrangement. The Milky Way is a spiral galaxy. That description is simple, but the reality behind it is anything but. At its centre lies a dense region packed with stars, gas, and a supermassive black hole. From that central bulge, vast spiral arms sweep outward in a flattened disk, curling gently like slow-moving pinwheels. These arms are not solid structures. They are regions where stars and gas bunch up slightly, forming waves of higher density that move through the disk over time. Our solar system sits well away from the centre, about halfway out along one of these spiral arms. We are not in a privileged position. We are not near the core, where conditions are crowded and extreme, nor are we at the far edge, where stars grow sparse. We occupy a quiet suburb of the galaxy, a region with enough stability for long-lived stars and planetary systems to exist. The scale of the Milky Way is difficult to grasp without comparison. From one side of the galactic disk to the other, the distance is roughly 100,000 light-years. That means a beam of light, moving faster than anything else in the universe, would need 100,000 years to cross it. The thickness of the disk is much smaller, only a few thousand light-years, giving the galaxy its flattened shape. Within this disk are hundreds of billions of stars. The exact number is uncertain because many are faint, small, or hidden behind clouds of dust. Some estimates suggest around 200 billion stars. Others push the number higher. Even the lower estimates place the Milky Way among the more massive galaxies in the local group. But stars are only part of the story. The Milky Way also contains vast clouds of gas and dust, the raw material for future stars and planets. These clouds trace the spiral arms and glow softly in radio and infrared wavelengths. They are cold, diffuse, and enormous, stretching across light years while remaining thinner than any vacuum humans can create on Earth. Surrounding the visible disk is something even larger and more elusive. The Milky Way is embedded in a massive halo of dark matter. This halo extends far beyond the region where stars are found, reaching hundreds of thousands of light years into space. It is the dark matter halo that gives the galaxy much of its mass and gravitational influence. Without dark matter, the Milky Way would not hold together as it does. The stars in the outer regions move too quickly to be bound by visible matter alone. Something unseen must be providing additional gravitational pull. That something is dark matter, and it dominates the galaxy's mass budget. This invisible halo is one of the reasons the Milky Way matters so much to the local group. Gravity does not care about light. It responds to mass. And when astronomers talk about the Milky Way as one of the anchors of the local group, they are largely referring to the mass contained in its dark matter halo. The Milky Way is not isolated within this halo. It is surrounded by smaller galaxies, many of them dwarf galaxies that orbit it like distant companions. Some of these are relatively well known, such as the Large and Small Magellanic Clouds, which are visible from the southern hemisphere as faint detached patches of light. Others are so dim that they were only discovered in recent decades through careful surveys. These satellite galaxies move along elongated orbits, sometimes plunging through the Milky Way's disk, sometimes lingering far out in the halo. Over time, many of them are gradually pulled apart by tidal forces. Their stars are stretched into long streams that wrap around the galaxy, forming ghostly traces of past mergers. This process is ongoing. The Milky Way is not a finished structure. It is still growing, still absorbing smaller galaxies, still reshaping itself through gravity. Every few billion years, a dwarf galaxy falls in and is slowly dismantled. Its stars become part of the Milky Way's halo, or disk, indistinguishable from stars that formed here long ago. This history of mergers is written into the motions of stars. Astronomers can trace stellar streams and identify groups of stars that share common origins. These remnants act like archaeological layers, preserving evidence of the galaxy's past interactions. In this way, the Milky Way serves as a record of how the local group has evolved over time. Understanding the Milky Way also helps clarify the scale of the local group itself. The galaxy's gravitational influence does not stop at the edge of its visible disk. It extends far outward, overlapping with the gravitational influence of neighbouring galaxies. In the space between the Milky Way and Andromeda, these gravitational fields interact, shaping the motions of smaller galaxies and dark matter alike. This overlapping influence creates a shared environment. The local group is not simply a collection of independent galaxies drifting near one another. It is a system where the largest members define regions of dominance, and smaller members respond accordingly. The Milky Way's role in this system is significant but not solitary. One way to think about it is to imagine hills and valleys in an invisible landscape shaped by gravity. The Milky Way sits in one of these valleys, Andromeda in another. Smaller galaxies roll slowly along the slopes, sometimes falling into one valley, sometimes lingering between them. The local group is the entire landscape, not just the deepest points. The motion of the Milky Way within this landscape is subtle, but measurable. Relative to the cosmic background our galaxy is moving, carried along by the gravitational pull of larger structures beyond the local group. At the same time, it is moving toward Andromeda, drawn by their mutual attraction. This inward motion tells us something important. The Milky Way and Andromeda are bound together. They are not drifting apart with the expansion of the universe. Their shared mass is sufficient to overcome that expansion locally. This fact alone defines the local group as a coherent structure rather than a temporary alignment. When astronomers estimate the total mass of the local group, they often rely heavily on the motion of the Milky Way and Andromeda. By measuring how fast these galaxies are approaching each other and how they influence nearby galaxies, scientists can infer how much mass must be present to produce those motions. The results consistently show that most of the mass is invisible. This means the Milky Way's importance extends beyond what we can see. Its dark matter halo likely overlaps with Andromeda's halo, forming a larger envelope that encompasses much of the local group. In a sense, the group is held together by a shared dark matter structure, with visible galaxies embedded like islands in a shallow sea. From within the Milky Way, this structure is impossible to perceive directly. Our view of the galaxy is limited by dust and perspective. We see the Milky Way edge-on, looking through its disk rather than down upon it. This makes mapping its full shape and size a challenging task that has taken generations of astronomers to refine. Despite these challenges, a consistent picture has emerged. The Milky Way is a large spiral galaxy, massive enough to shape its surroundings, but not so dominant that it overwhelms the entire group. It shares the local group with another giant, and together they define the group's character. This balance matters. If the Milky Way were much more massive, it might have already absorbed many of its neighbours. If it were much smaller, it might itself be a satellite of Andromeda. Instead, the two exist in a kind of gravitational partnership, slowly drawing closer over time. That future interaction is already encoded in the present. The approach of Andromeda is not speculative. It is measured, and it implies that the Milky Way's role in the local group will change dramatically in the distant future. The galaxy we call home will not remain as it is forever. Its spiral arms will be distorted, its stars will be redistributed, its identity will evolve. Yet even this eventual transformation does not diminish the Milky Way's current significance. Right now, it is one of the main reference points for understanding the local group. Its mass, structure, and motion provide clues about the group's size and boundaries. Looking outward from the Milky Way, beyond the familiar haze of our own stars and dust, there is another galaxy that quietly dominates our local cosmic neighbourhood. You cannot see it with the naked eye unless the sky is very dark and your patience is generous, yet it is there, vast and luminous, approaching us slowly through space. This is Andromeda, the giant next door, and its presence reshapes everything we mean when we talk about the size and nature of the local group. Andromeda is not just another galaxy nearby. It is the largest and most massive member of the local group, slightly outweighing the Milky Way and extending its influence across millions of light years. While we tend to think of our own galaxy as the main character in our cosmic story, Andromeda has every claim to that role as well, and in some ways, an even stronger one. From Earth, Andromeda appears as a faint smudge in the sky, a soft oval glow barely brighter than the background darkness. That modest appearance is deeply misleading. What you're seeing is the combined light of hundreds of billions of stars spread across an enormous distance. The photons entering your eyes tonight left Andromeda roughly 2.5 million years ago, long before the first humans ever looked up and wondered what those lights might be. The sheer size of Andromeda is difficult to overstate. Its visible disk stretches over 200,000 light-years from edge to edge, making it significantly larger than the Milky Way. Its stellar halo extends even farther, with sparse stars reaching out to distances that rival the separation between the two galaxies themselves. When astronomers map Andromeda in detail, they find streams, shells, and extended structures that speak of a long and active history. Like the Milky Way, Andromeda is a spiral galaxy. It has a central bulge, a flattened disk, and sweeping spiral arms where gas and dust give rise to new stars. But the proportions are different. Andromeda's bulge is larger and more massive, suggesting a more turbulent past. Its disk contains vast reservoirs of stars, many older on average than those in the Milky Way, hinting at differences in how the two galaxies evolved. At the heart of Andromeda lies a supermassive black hole, even larger than the one at the centre of our own galaxy. This black hole is quiet by cosmic standards, not actively feeding or blazing with radiation, but its presence adds to the overall mass that defines Andromeda's gravitational reach. Surrounding the visible galaxy is an enormous halo of dark matter, far larger than the luminous disk. This halo is the true engine of Andromeda's influence. It extends hundreds of thousands of light years in all directions, overlapping with the dark matter halo of the Milky Way. In this overlapping region, gravity becomes a shared affair, shaping the motion of smaller galaxies and matter throughout the local group. This overlap is one of the reasons Andromeda is so important when asking how big the local group really is. The group is not defined by the edges of visible galaxies, but by the reach of their combined gravitational fields. Andromeda's mass pushes that reach outward, enlarging the region where galaxies remain bound and slowing the expansion of space locally. Andromeda is accompanied by its own system of satellite galaxies. Dozens of dwarf galaxies orbit it, some in tight clusters, others in elongated paths that carry them far into intergalactic space before pulling them back again. Many of these satellites show signs of disruption, their stars stretched into streams by Andromeda's gravity. These streams are not random. They trace Andromeda's past interactions, marking where smaller galaxies have fallen in and been torn apart over billions of years. In some cases, astronomers can reconstruct these events, identifying which stars once belonged to which smaller systems before they were absorbed. This history matters because it tells us that Andromeda, like the Milky Way, has grown through mergers. It didn't form all at once. It accumulated mass gradually, capturing smaller galaxies and incorporating them into its structure. Each merger added stars, gas, and dark matter, increasing Andromeda's size and influence. In fact, evidence suggests that Andromeda may have experienced more dramatic mergers than the Milky Way. Its stellar halo is more massive and more complex, indicating a richer history of accretion. This could explain why Andromeda is slightly larger and more massive today. Despite their similarities, Andromeda and the Milky Way are not identical twins. They are more like siblings who grew up in the same neighbourhood but had different experiences. These differences are important for understanding the local group as a whole, because they show how varied galaxy evolution can be even within a shared environment. One of the most significant facts about Andromeda is its motion relative to us. Careful measurements show that Andromeda is moving toward the Milky Way at a speed of about 100 kilometers per second. This motion is not caused by the general expansion of the universe. It is a result of mutual gravitational attraction. This inward motion tells astronomers that the Milky Way and Andromeda are gravitationally bound to each other. They are not drifting apart. They are approaching, slowly but inexorably, on a collision course that will culminate several billion years from now. That future encounter is often described as a collision, but it is better thought of as a merger. The galaxies will pass through one another, their stars mostly missing each other due to the vast distances between them. Over time, their disks will be distorted, their gas clouds will collide and form new stars, and their structures will gradually blend into a single, larger galaxy. This eventual merger has implications for the local group's size. As the two largest members come together, the group will become more centrally concentrated. Smaller galaxies will be drawn inward, and the region of dominant gravitational influence may shrink even as the total mass remains the same. But that is far in the future. Right now, the Milky Way and Andromeda remain distinct, separated by a gulf of intergalactic space filled with thin gas, dark matter, and faint traces of stars. This space is part of the local group too, even though it appears empty at first glance. The region between the two galaxies is where their gravitational fields meet and overlap. It is here that the local group's character becomes most apparent. This is not empty space in the everyday sense. It is structured, shaped by invisible mass, and slowly evolving. Understanding Andromeda also helps clarify what astronomers mean when they talk about the local group's centre. Because the Milky Way and Andromeda are similar in mass, the centre of gravity of the local group lies somewhere between them, not inside either galaxy. This shared centre influences the motion of all group members. Smaller galaxies often orbit this shared centre, rather than one dominant galaxy alone. Their paths reflect the combined gravitational pull of both giants. This is one reason the local group cannot be understood by looking at the Milky Way in isolation. Andromeda's presence is equally important. The distance to Andromeda also provides a useful yardstick for thinking about scale. 2.5 million light-years is the distance light travels in 2.5 million years. If you could somehow travel at the speed of light, it would take longer than the entire history of human civilization just to reach Andromeda. And yet, within the local group, this distance is relatively small. Other galaxy groups and clusters span tens or hundreds of millions of light years. The local group is modest by comparison, but Andromeda's scale ensures that it is still vast beyond everyday comprehension. Another subtle but important point is visibility. Andromeda is one of the few galaxies outside the Milky Way that can be seen without a telescope. This fact has had a profound effect on astronomy. For centuries, Andromeda was known as a faint nebula, its true nature unknown. It was only in the 20th century that astronomers confirmed it was a separate galaxy far beyond the Milky Way. That discovery expanded our understanding of the universe dramatically. It revealed that the Milky Way was not the entire universe, but one galaxy among many. In a sense, Andromeda helped humanity realize just how big its surroundings truly were. This realization continues to echo in how we think about the local group today. Andromeda is a reminder that even our nearest neighbours are unimaginably distant, and yet still close enough to interact over cosmic time. It embodies the balance between vastness and connection that defines the group. As we look ahead, Andromeda's role will only grow more significant. Its merger with the Milky Way will reshape the local group's future. The combined galaxy that results will dominate the region even more strongly, altering the paths of smaller galaxies and redefining what local means in cosmic terms. For now, though, Andromeda remains a separate presence, a silent giant moving closer with each passing moment. Its gravity stretches across space, its dark matter halo overlapping with ours, its stars shining steadily across millions of years. Understanding Andromeda helps anchor our sense of scale. It shows that the local group is not centered on us alone. It is a shared domain, shaped by at least two massive galaxies whose combined influence defines its size and structure. Shift your attention slightly away from the two dominant spirals, and the local group begins to feel less like a duet and more like a small ensemble. There is another substantial galaxy here, not as massive as Andromeda, not as familiar to us as the Milky Way, but still large enough to matter in the gravitational choreography of this region. This is the Triangulum galaxy, often overlooked, sometimes described as secondary, yet quietly significant in understanding how big the local group truly is. The Triangulum galaxy, also known as Messier 33, lies roughly 3 million light-years from the Milky Way. In the sky, it appears fainter than Andromeda, smaller in apparent size and more difficult to spot without optical aid. But that faintness is more about distance and orientation than importance. Triangulum is the third largest member of the local group, and its mass, though modest compared to the two giants, is still immense by any ordinary measure. Triangulum is a spiral galaxy, like the Milky Way and Andromeda, but it lacks the large central bulge that defines its bigger neighbours. Its structure is more delicate. The spiral arms are open and loosely wound, rich with bright regions of active star formation. In fact, Triangulum is known for containing one of the largest star-forming regions in the entire local group, a vast glowing cloud where new stars are being born in large numbers. That detail is not just decorative. It tells us that Triangulum has had a somewhat different evolutionary path. Its smaller mass means its gravitational pull is weaker. It has likely experienced fewer dramatic mergers than Andromeda, and perhaps fewer than the Milky Way. As a result, its disk remains relatively undisturbed, and its star formation continues at a steady pace. When astronomers measure the diameter of Triangulum's visible disk, they find it spans roughly 60,000 light-years. That makes it smaller than the Milky Way, but still enormous in human terms. Its total mass is estimated to be around 10% of the Milky Way's mass, including its dark matter halo. Even at that reduced scale, the numbers involved are staggering. Triangulum also possesses its own halo of dark matter, extending far beyond its visible stars. This halo overlaps with the larger dark matter environment of the local group, contributing to the overall gravitational landscape. Though it does not dominate the group in the way the Milky Way or Andromeda do, it still shapes the motions of nearby smaller galaxies. One of the intriguing aspects of triangulum is its relationship with Andromeda. Observations suggest that triangulum may be gravitationally bound to Andromeda, orbiting it to significant distance. If this is true, then triangulum is not an entirely independent third anchor of the local group, but rather a major satellite of the largest member. That possibility changes how we think about the group structure. Instead of 3 equal pillars, we may have 2 primary centres of mass, with the third galaxy leaning more toward one than the other. Yet even as a satellite, triangulum is substantial enough to influence Andromeda's outer regions and to carry its own system of smaller companions. Triangulum has at least a handful of known dwarf galaxies associated with it. These smaller systems orbit at distances of tens of thousands of light-years, tracing out the gravitational influence of triangulum's dark matter halo. This nested hierarchy, dwarf galaxies orbiting triangulum, which in turn orbits within the local group's shared environment, illustrates how layered and complex the group really is. From our vantage point inside the Milky Way, triangulum is positioned roughly in the same general direction as Andromeda in the sky, though slightly offset. Its light has been travelling toward us for millions of years, crossing the intergalactic medium that fills the local group. That medium is not entirely empty. It contains thin gas and traces of matter, shaped by the gravitational interplay of the group's major members. The motion of triangulum through this environment provides valuable clues about the total mass of the local group. By measuring its velocity and direction, astronomers can infer how much gravitational pull must be present to keep it bound within the system. These measurements contribute to estimates of the group's overall size and mass. Triangulum's relatively undisturbed structure also offers a kind of control case. While Andromeda shows signs of significant mergers in its past, and the Milky Way reveals evidence of accreted dwarf galaxies, triangulum appears to have evolved more gently. Comparing these histories helps astronomers understand how interactions shape galaxies within a shared gravitational domain. Another important point is scale perception. When discussing the local group, it is easy to focus only on the 2 largest galaxies and imagine everything else as minor detail. But triangulum reminds us that even the third member is a vast spiral system in its own right. Its inclusion stretches the effective span of the local group outward. If you draw an imaginary triangle connecting the Milky Way, Andromeda and triangulum, the distances involved span several million light-years. This geometric arrangement alone gives a sense of the group's scale, and that triangle does not represent the outer boundary. It represents only the most luminous anchors within a much larger gravitational envelope. Triangulum's quietness, in comparison to its neighbours, does not mean it lacks importance. In some ways, its subtle role makes it more informative. Because it is smaller, its motions are more sensitive to the gravitational field of the local group as a whole. It acts like a test particle, responding to the combined mass of the system. The existence of triangulum also reinforces the idea that the local group is not centred on the Milky Way. We are not at the core of this arrangement. The centre of mass lies somewhere between the major galaxies, influenced by their relative masses and distances. Triangulum's position shifts that balance slightly, adding weight to the Andromeda side of the equation. When astronomers model the future of the local group, triangulum often plays a supporting role. It is likely to participate in the eventual merger between the Milky Way and Andromeda. Depending on its orbit, it may collide with one of them before the 2 giants merge, or it may be drawn into the combined system afterward. That future underscores something about the local group's nature. It is dynamic. It is evolving. The quiet third member will not remain quiet forever. Over billions of years, its stars will be redistributed, its structure altered, and its identity folded into a larger whole. For now, though, triangulum continues its steady orbit, forming new stars in its spiral arms, glowing softly across millions of light years. Its presence enlarges our cosmic neighbourhood. Without it, the local group would still be vast, but its geometry would be simpler, its gravitational landscape less intricate. In practical terms, including triangulum in our mental map of the local group extends our sense of local space outward. It reminds us that our immediate galactic environment is not a pair but a trio, and beyond that trio lies a swarm of smaller companions whose motions weave through this shared gravitational field. Once you move past the large spirals, the Milky Way, Andromeda and Triangulum, the local group begins to change character. It becomes quieter, dimmer, and far less obvious. This is where most of the group's members reside, not as grand pinwheels of stars, but as faint, fragile systems scattered through the dark. These are the dwarf galaxies, and without them, our understanding of how big the local group really is would be incomplete. Dwarf galaxies are exactly what their name suggests, smaller than the dominant galaxies by orders of magnitude. But smaller does not mean insignificant. In fact, they are the most numerous type of galaxy in the universe, and they make up the vast majority of members in the local group. While the Milky Way and Andromeda command attention through brightness and size, dwarf galaxies quietly define the group's true extent. Most dwarf galaxies in the local group contain anywhere from a few thousand to a few billion stars. That may sound like a lot, but compared to the hundreds of billions of stars in a large spiral galaxy, it is a modest population. Many dwarfs are so faint that they are nearly invisible against the background of space. Some were only discovered in the last few decades, and others may still be waiting to be found. From Earth, dwarf galaxies do not announce themselves. They do not glow brightly or display dramatic spiral arms. Many appear as diffuse smudges, barely distinguishable from noise in astronomical images. Detecting them requires careful analysis, long exposures, and often indirect methods such as tracking the motion of stars. Despite their faintness, dwarf galaxies play an outsized role in defining the local group's size. They occupy the outskirts of the group, tracing how far its gravitational influence reaches. If a dwarf galaxy is gravitationally bound, moving slowly enough to remain part of the group, rather than drifting away with cosmic expansion, it helps mark the boundary of what belongs to the local group. Some dwarf galaxies orbit close to larger galaxies. The Milky Way alone has dozens of known satellite dwarfs. The Large and Small Magellanic Clouds are the most prominent examples, visible without telescopes from the southern hemisphere. They are irregular in shape, rich in gas and actively forming stars. But beyond these bright companions lies a swarm of much smaller satellites, many of them extremely faint. These faint satellites often appear stretched and distorted. Gravity from the Milky Way pulls on them, elongating their shapes and slowly stripping away stars. Over time, these stars form long streams that wrap around the galaxy, becoming part of its halo. In this way, dwarf galaxies are gradually dismantled, contributing their material to larger systems. Andromeda hosts a similar population of dwarf companions, perhaps even more numerous than those of the Milky Way. Observations reveal a complex arrangement of satellites, some clustered in planes, others scattered more randomly. This distribution has raised interesting questions about how dwarf galaxies form and how they are captured. Triangulum, too, has its own smaller companions, though fewer in number. Even so, the pattern repeats. Larger galaxies sit at the centres of gravitational wells, surrounded by smaller systems that orbit, interact, and sometimes merge. But not all dwarf galaxies are tied closely to a single large galaxy. Some roam the local group more freely, occupying the space between the major members. These isolated dwarves are especially valuable to astronomers because their motions reflect the gravitational pull of the group as a whole, rather than the influence of one dominant galaxy. These free-floating dwarfs help map the local group's gravitational landscape. By measuring how they move, scientists can estimate how much mass is present in different regions of the group, including mass that cannot be seen. In this way, dwarf galaxies act as test particles, revealing the invisible structure underlying the visible one. One of the most surprising discoveries about dwarf galaxies is how much dark matter they contain. In many cases, the visible stars make up only a tiny fraction of the galaxy's total mass. The rest is dark matter, outweighing the stars by factors of 10 100, or even more. This makes dwarf galaxies some of the most dark matter-dominated objects known. Their stars move faster than they should if visible matter were the only source of gravity. The conclusion is unavoidable. Dark matter must be present in large quantities, holding these faint systems together. Because of this, dwarf galaxies are central to efforts to understand dark matter itself. Their simplicity, relative to large spirals, makes them useful laboratories. They lack complex structures like spiral arms or dense central bulges, which can complicate measurements. Instead, their motions offer relatively clean signals of gravitational effects. The presence of so many dwarf galaxies also complicates the question of how big the local group is. If we only counted large galaxies, the group might seem compact and tidy. Once dwarf galaxies are included, the picture expands dramatically. The local group becomes a sprawling, loosely connected system extending across millions of light-years. Some dwarf galaxies lie at distances of over 3 million light-years from the Milky Way. Others are found near the theoretical boundary, where the local group's gravity gives way to the expansion of the universe. These boundary dwellers are particularly important. Their motions help define the zero-velocity surface, the region where gravity and cosmic expansion balance. Beyond this surface, galaxies are no longer bound. They drift away, carried by the stretching of space itself. Inside it, galaxies remain part of the local group's shared destiny. Dwarf galaxies near this boundary mark the transition between local structure and the broader universe. Not all dwarf galaxies look alike. Some are irregular, with patchy star formation and chaotic shapes. Others are spheroidal, smooth and gas-poor, containing mostly old stars. These differences often reflect their environment. Dwarfs that orbit close to large galaxies tend to lose their gas through gravitational interactions, halting new star formation. More isolated dwarfs often retain gas and continue forming stars. This environmental influence highlights how the local group operates as a system. The larger galaxies shape the evolution of smaller ones, not through sudden violence, but through persistent gravitational pressure. Over time, this pressure transforms dwarfs, stripping them down and altering their structure. The faintest dwarf galaxies push the limits of detectability. Some contain only a few thousand stars, spread thinly over large volumes of space. These ultrafaint dwarfs are among the least luminous galaxies known. Yet even they appear to be embedded in dark matter halos, suggesting that dark matter clumps on very small scales. The discovery of these ultra-faint dwarfs has expanded the known population of the local group in recent years. Each new detection slightly enlarges the group's apparent size, both in terms of membership and spatial extent. It also raises questions about how many more remain hidden. Astronomers suspect that many dwarf galaxies have already been destroyed. Over billions of years, gravitational interactions have torn them apart, leaving behind only stellar streams or dispersed stars. These remnants are difficult to identify, but their existence implies that the local group was once even richer in small galaxies than it is today. This gradual loss does not mean the local group is shrinking in size, but it does change its appearance. As dwarfs are absorbed, their material spreads out, contributing to the halos of larger galaxies and to the diffuse background of stars within the group. Dwarf galaxies also provide insight into the local group's early history. Many contain very old stars, formed shortly after the universe itself began. These stars preserve information about the conditions of the early cosmos, including chemical composition and star formation rates. By studying dwarf galaxies, astronomers can reconstruct how the local group assembled over time. They can trace which galaxies formed first, which fell in later, and how the group's mass grew. This historical perspective adds depth to our understanding of the group's scale. It is not just large in space, but long in time. From a human perspective, dwarf galaxies are humbling. They remind us that size and brightness are not the only measures of importance. These faint systems, barely visible across millions of light-years, hold clues to fundamental questions about matter, gravity, and cosmic structure. they also reinforce how misleading our intuitive sense of scale can be. A galaxy with 1 million stars sounds enormous, yet in the local group it is considered small. A distance of 1 million light-years sounds vast, yet within this group it is routine. As more dwarf galaxies are discovered, the local group continues to grow in perceived size and complexity. Each new member extends the map slightly farther, revealing a system that is more expansive and more intricate than earlier generations imagined. All of this brings us back to the central question: how big is the local group really? The answer depends on whether you focus on the bright centres or the faint outskirts. Dwarf galaxies occupy those outskirts, stretching the group's boundaries into regions that appear almost empty at first glance. They are the quiet companions in the dark, shaping the local group not through brilliance, but through presence. Their slow motions, faint light, and heavy dark matter halos define the edges of our cosmic neighbourhood. Once you start looking beyond the bright familiar galaxies and into the faint population of dwarfs, a deceptively simple question becomes surprisingly difficult to answer. How many galaxies are actually in the local group? At first glance, it sounds like something that should have a clean number attached to it, a tidy figure you could write down and move on from. In practice, that number is constantly shifting, debated, revised, and quietly expanded as our ability to observe the universe improves. Right now, astronomers estimate that the local group contains a little more than 50 confirmed galaxies. Some lists give numbers in the low 50s, others creep closer to 60. And even those figures are usually followed by a careful qualifier: known galaxies, confirmed members, current census. All of those phrases hint at an important truth: the count is not finished. The difficulty begins with defining what we mean by a galaxy in the first place. In the early days of astronomy, a galaxy was something large, bright, and clearly separate from individual stars. That definition worked when telescopes were limited, and only the most prominent systems could be seen. As instruments improved, that definition began to blur. Objects once dismissed as star clusters turned out to be small galaxies. Others fell into a grey area, sharing properties of both. Modern astronomy defines a galaxy not just by brightness or size, but by gravitational behaviour. A galaxy must be a system of stars bound together by gravity and embedded in its own dark matter halo. This last requirement turns out to be crucial, and also deeply inconvenient. Dark matter cannot be seen directly, so its presence must be inferred from how stars move. That inference becomes more uncertain as galaxies become smaller and fainter. Some of the faintest objects in the local group contain only a few thousand stars. Their total light output is so low that they can be easily confused with dense star clusters. The only way to tell them apart is to measure how fast their stars move. If the stars are moving too quickly to be held together by visible matter alone, astronomers conclude that dark matter must be present, and the object is classified as a galaxy. This means that the galaxy count depends heavily on how carefully we look and how precisely we measure. Each improvement in telescope sensitivity, data analysis, or sky coverage brings the possibility of new discoveries. Over the past 2 decades, the number of known local group galaxies has increased significantly, not because the group has changed, but because our ability to detect its faintest members has improved. Many of the galaxies in the local group were unknown until relatively recently. The ultra-faint dwarf galaxies discovered in the last 20 years have dramatically altered the census. These galaxies are not just dim, they are spread thinly across space, with stars separated by large distances, making them difficult to distinguish from the background. Some of these ultra-faint dwarfs are so subtle that they were discovered not by looking directly at them, but by analysing large surveys of individual stars. Astronomers notice slight overdensities of stars moving together, like faint whispers of structure in an otherwise random field. Only after careful analysis did these overdensities reveal themselves as galaxies. Each time one of these discoveries is confirmed, the question arises again: How many more are out there? The answer is almost certainly more than we know. The distribution of galaxies within the local group is also uneven. The Milky Way and Andromeda host the majority of known satellites. This could reflect real differences in how these galaxies formed and evolved. It could also reflect observational bias. We live inside the Milky Way, and Andromeda is relatively close and well studied. Smaller galaxies farther away, especially those not orbiting a large spiral, are harder to detect. This bias means that our census is likely incomplete, particularly toward the edges of the local group. Isolated dwarf galaxies in the outer regions are faint, spread out, and difficult to separate from background objects. Some may remain undiscovered simply because we have not looked closely enough in the right places. There is also the question of former members. Over billions of years, many dwarf galaxies have been absorbed by larger ones. Their stars have been stretched into streams or mixed into galactic halos. These galaxies no longer exist as separate entities, but they were once part of the local group. If we were counting historically rather than presently, the number would be much higher. This raises a subtle point about what the number of galaxies actually represents. Are we counting current, gravitationally distinct systems? Or are we counting all the galaxies that have ever belonged to this region? Most astronomical catalogues focus on the present, but understanding the local group's size and complexity requires remembering that it is a system in motion. Even among current members, classification can change. Objects once considered galaxies have been reclassified as star clusters, and vice versa. As measurements improve, boundaries shift. This fluidity means that any number you hear should be understood as provisional rather than final. Another complication comes from the local group's boundary itself. Some galaxies sit near the edge of the group, where gravity and cosmic expansion are in balance. Their motions are slow and ambiguous. Are they bound to the local group, or are they already drifting away? Different studies sometimes reach different conclusions. A galaxy's membership is determined by its velocity relative to the group's center of mass. Some galaxies appear on one list, and some galaxies appear on one list and disappear from another. This uncertainty affects the total count. Depending on where you draw the boundary and how strict you are, the local group might have a few members more or fewer. These differences may seem minor, but they matter when trying to understand the group's true size and mass. The sheer variety of galaxies in the local group also complicates the count. There are spiral galaxies, irregular galaxies, spheroidal galaxies, and transitional types that do not fit neatly into any category. Some dwarves are actively forming stars, others are ancient and inert, some are gas-rich, others have been stripped nearly bare. Each type has a different visibility profile. Star-forming galaxies are easier to detect because they contain bright young stars. Older, gas-poor dwarfs fade into the background. This means the faintest and oldest members are likely undercounted. Astronomers also face challenges posed by our own galaxy. The Milky Way's disk is filled with dust that obscures our view of distant objects. This region, known as the zone of avoidance, hides a portion of the sky where galaxies are harder to detect. Some local group members may lie behind this veil, waiting to be uncovered. Radio observations can sometimes peer through this dust, but even then, detecting faint dwarf galaxies remains difficult. As new surveys expand coverage and sensitivity, it is likely that additional members will be found in these obscured regions. Simulations of galaxy formation offer another perspective. When scientists model how structures like the local group form in a universe dominated by dark matter, they often predict more dwarf galaxies than we currently observe. This discrepancy is known as the missing satellites problem. There are several possible explanations. Some dwarf galaxies may be too faint to detect. Others may have failed to form stars at all, existing as dark matter halos with little or no visible matter. These hypothetical dark galaxies would be nearly invisible, detectable only through their gravitational effects. If such objects exist in significant numbers, the true population of the local group could be much larger than the visible count suggests. In that case, Asking how many galaxies are in the local group becomes even more complex. The answer would depend on whether you count only luminous systems or include dark ones as well. Even if we restrict ourselves to visible galaxies, the number is not static. New discoveries continue to add to the list. Improved surveys, especially those mapping large areas of the sky with high sensitivity, are likely to reveal additional faint members in the coming years. This evolving census reflects a broader truth about astronomy. Our picture of the universe is always incomplete, always provisional. Each answer opens the door to further questions. Each improvement in technology reshapes what we think we know. From a broader perspective, the exact number of galaxies may be less important than what their distribution tells us. The fact that the local group contains dozens of galaxies spread across millions of light years highlights its scale. It is not a small cluster of a few large objects. It is a loose, extended system with many components. The dominance of dwarf galaxies also tells us something fundamental about cosmic structure. Large galaxies are rare. Small ones are common. The local group is typical in this respect, reflecting patterns seen throughout the universe. Understanding this helps place our home galaxy in context. It also underscores how misleading brightness can be. The galaxies that dominate our imagination are not the ones that dominate in number. The faint companions, barely visible against the dark, make up the bulk of the group. As the census grows, so does our sense of the local group's true size. Each new galaxy extends the known boundaries slightly farther, filling in what once seemed empty space. Over time, the group appears less like a sparse handful of islands and more like a broad archipelago scattered across a dark sea. This gradual filling in has a calming quality to it. Space does not suddenly become crowded. It becomes quietly populated, one faint object at a time. The local group reveals itself not through dramatic discovery, but through patient observation. So how many galaxies are actually in the local group? The most honest answer is that we do not yet know for sure. The current count sits a little above 50, but that number is almost certainly incomplete. Future discoveries will add to it. Reclassifications may subtract or rearrange it. The boundary itself may shift. What we can say with confidence is that the local group is far richer and more complex than it first appears. Its size is defined not just by distance, but by membership, and membership is a subtle, evolving concept. Once the question shifts from how many galaxies there are to where they actually are, the scale of the challenge changes completely. Counting galaxies in the local group is difficult enough, but measuring the distances between them is a deeper problem, one that has occupied astronomers for more than a century. These distances are not just large, they are far beyond anything that can be measured directly. No ruler stretches across intergalactic space. No signal can be bounced there and back in a useful way. Instead, astronomers rely on a layered set of techniques, each one extending the reach of the last, building a map of the local group step by careful step. The difficulty begins with something deceptively simple. From Earth, the universe appears flat. Stars, nebulae, and galaxies are projected onto the sky like points on a dome. Depth is not immediately visible. Two objects that appear close together may in fact be separated by millions of light years. To understand the local group as a three-dimensional structure, astronomers must find ways to recover that missing depth. The most basic method of measuring distance in astronomy is parallax. This is the same principle your eyes use to judge distance in everyday life. Hold a finger out in front of you and close one eye, then the other. The finger appears to shift against the background. The closer it is, the larger the shift. Astronomers use this same idea, but instead of two eyes, they use Earth's orbit around the Sun. As Earth moves from one side of its orbit to the other over the course of 6 months, nearby stars appear to shift slightly against the background of more distant stars. This tiny shift, measured in fractions of an arcsecond, allows astronomers to calculate distance using simple geometry. Parallax is elegant, reliable, and fundamentally limited. Beyond a few thousand light years, the shifts become too small to measure accurately, even with modern instruments. Parallax works beautifully for mapping the Milky Way, but it barely scratches the surface of the local group. The nearest galaxy outside our own lies more than 2 million light-years away, far beyond the reach of parallax. To go farther, astronomers must turn to indirect methods, using objects of known brightness as distance markers. These markers are known as standard candles. The idea is straightforward. If you know how bright something truly is, and you can measure how bright it appears from Earth, the difference tells you how far away it must be. The challenge lies in finding objects whose true brightness is well understood and consistent. One of the most important standard candles for mapping the local group is a type of star called a Cepheid variable. These stars pulse in brightness at regular intervals. The key discovery, made in the early 20th century, was that the period of a Cepheid's pulsation is directly related to its intrinsic brightness. Measure how fast it pulses, and you know how bright it really is. Cepheid variables are luminous enough to be seen in nearby galaxies, including Andromeda and Triangulum. By identifying Cepheids in these galaxies and measuring their periods and apparent brightness, astronomers can calculate distances with relatively high precision. This method was crucial in establishing that Andromeda lies far beyond the Milky Way, confirming that it is a separate galaxy rather than a nearby cloud of gas. Cepheids form one of the rungs on what astronomers call the cosmic distance ladder. Each rung extends measurement farther than the previous one, but each also depends on the accuracy of the rung below it. Parallax calibrates Cepheids. Cepheids calibrate more distant methods. Errors can propagate upward, which is why careful cross-checking is essential. Beyond Cepheids, astronomers use other types of standard candles. One important example within the local group is the tip of the red giant branch. Red giant stars reach a predictable maximum brightness before undergoing changes in their internal structure. This maximum brightness is nearly the same for all such stars, making it a useful distance indicator. Red giant stars are common and relatively bright, making them easier to find in dwarf galaxies where Cepheids may be rare or absent. By identifying the brightest red giants in a galaxy and comparing their observed brightness to the expected value, astronomers can estimate distance. This method has become a workhorse for mapping the local group's many faint members. Another tool involves planetary nebulae, glowing shells of gas ejected by dying stars. These objects have characteristic brightness distributions that can be used statistically to infer distance. While less precise than Cepheids or red giants, they provide additional checks and help refine the overall map. All of these methods rely on light, but light is not always cooperative. Dust within galaxies can absorb and scatter light, making objects appear dimmer than they really are. If not corrected for, this can lead to overestimating distances. Astronomers must carefully account for dust effects, using observations at different wavelengths and models of interstellar material. Measuring distance also requires knowing which stars belong to which galaxy. This is not always obvious, especially for dwarf galaxies with sparse stellar populations. Astronomers use motion, chemical composition, and spatial clustering to distinguish member stars from foreground or background objects. Each step introduces uncertainty, which must be managed and minimized. Once distances are measured, they can be combined with velocity information to paint a dynamic picture of the local group. Velocities are typically measured using the Doppler effect, observing how the light from a galaxy is shifted toward the red or blue end of the spectrum depending on its motion relative to Earth. For nearby galaxies, these velocities are not dominated by cosmic expansion. Instead, they reflect local gravitational interactions. By combining distance and velocity data, astronomers can determine whether a galaxy is bound to the local group or drifting away. This distinction is critical for defining the group's true size. Some galaxies lie at ambiguous distances and velocities, hovering near the boundary where gravity and expansion balance. Measuring their distances accurately can tip the classification one way or the other. In this sense, distance measurement is not just a technical exercise. It directly shapes our understanding of what belongs to the local group. Over time, distance measurements have become more precise. Space-based observatories have eliminated atmospheric distortion, allowing finer resolution and deeper surveys. Improvements in detectors and data analysis have reduced uncertainties and revealed faint stellar populations previously hidden. Despite these advances, distance measurement remains one of the largest sources of uncertainty in astronomy. Different methods sometimes yield slightly different results. Reconciling these differences requires careful calibration and comparison. Astronomers often use multiple independent techniques for the same galaxy to increase confidence. The local group benefits from this approach because it's close enough for several methods to overlap. Cepheids, red giants, and other indicators can all be applied within this region, providing a robust framework. Farther out, such redundancy becomes harder, and uncertainties grow. Understanding distances also reveals the sheer emptiness of the local group. Even though it contains dozens of galaxies, the average separation between them is enormous. Millions of light-years of space lie between the major members. Within that space is a thin intergalactic medium, composed of sparse gas and dark matter, nearly invisible but dynamically important. Distance measurements help quantify this emptiness. They show that galaxies are not packed tightly together, but instead float in a vast volume. This loose arrangement is one reason the local group is considered a group rather than a cluster. Clusters are denser, with galaxies separated by smaller distances and interacting more frequently. Mapping the local group in 3 dimensions also reveals its overall shape. It is not spherical, it is elongated, with galaxies distributed along a rough axis connecting the Milky Way and Andromeda and extending outward through the region. This shape reflects the underlying distribution of dark matter and the history of how the group assembled. As distance measurements improve, this shape becomes clearer. New members are placed more accurately within the map. The boundaries become better defined, though still fuzzy. The local group emerges not as a sharply bounded object, but as a region with gradients of influence. There is also a temporal dimension to distance measurement. Light takes time to travel. When we observe a galaxy 2 million light-years away, we see it as it was 2 million years ago. For the local group, this time delay is modest compared to cosmic timescales, but it still means we are looking slightly into the past. This matters when studying star formation, mergers, and structural changes. Distance measurement anchors these observations in a timeline, allowing astronomers to reconstruct how galaxies have evolved together. The local group is not frozen in time. It is observed in motion, even if that motion is slow. Distance also sets scale for everything else. Mass estimates, size estimates, and gravitational models all depend on accurate distances. If a galaxy is farther than thought, it is larger and more massive than assumed. If it is closer, the opposite is true. Small errors in distance can ripple through many aspects of analysis. This is why astronomers devote so much effort to refining distance measurements. The local group serves as a testing ground for these techniques. Success here builds confidence in applying them farther out into the universe. From a broader perspective, measuring the distance between galaxies changes how we relate to space itself. It replaces vague notions of far and near with quantified relationships. It transforms the night sky from a flat tapestry into a structured landscape with depth and scale. Within the local group, this landscape spans millions of light years, filled mostly with darkness, punctuated by islands of stars. Distance measurement turns that darkness into something measurable, something that can be charted and understood. As we continue, these measurements lead naturally to another question. Once distances are known, how do astronomers translate those numbers into a sense of scale? Numbers alone do not always help. You can say that the Milky Way is 100,000 light-years across, that Andromeda lies 2.5 million light-years away, that the local group spans several million light-years from one side to the other, and still the mind quietly refuses to cooperate. A light year sounds manageable, almost friendly. But what it represents is distance so extreme that ordinary intuition simply stops working. So before we move farther outward, it helps to slow down and gently unpack what these units really mean and how gravity stitches them together into something coherent. A light year is not a measure of time. Despite the name, it is a measure of distance. It is the distance light travels in 1 year, moving at about 300,000 kilometers per second. In a single second, light circles the Earth more than 7 times. In 1 minute, it travels farther than the distance between Earth and the Moon. In a year, it covers nearly 10 trillion kilometers. 10 trillion kilometers is not a number we can feel. It is too large to imagine walking, flying, or driving. If you could travel at the speed of a commercial airplane, reaching the nearest star outside our solar system would take millions of years. Even at the speed of our fastest spacecraft, it would take tens of thousands of years. Light years exist because anything smaller quickly becomes impractical. Within the local group, distances are measured in millions of light years. The gap between the Milky Way and Andromeda is roughly 2.5 million light years. That means the light entering telescopes tonight left Andromeda long before humans built cities, long before written language, long before agriculture. When you look at Andromeda, you are seeing ancient light, crossing intergalactic space uninterrupted for millions of years. But light years only tell us how far apart galaxies are. They do not tell us why those galaxies remain connected. That connection comes from gravity. Gravity is subtle across small distances. You barely notice the gravitational pull of a building, a mountain, or even a city. On cosmic scales, gravity is the architect of structure. It gathers gas into stars, stars into galaxies, galaxies into groups. Without gravity, the local group would not exist. Its members would drift apart as space expands. The universe as a whole is expanding. Distant galaxies are receding from us, carried by the stretching of space itself. But within the local group, gravity is strong enough to resist that expansion. The combined mass of the Milky Way, Andromeda, triangulum, and their dark matter halos creates a gravitational well deep enough to hold the group together. This is where scale becomes interesting. The local group spans roughly 10 million light-years from one side to the other, depending on how you define its boundary. That means light would take 10 million years to cross it. Yet within that enormous region, gravity still wins over cosmic expansion. To understand why, it helps to think in terms of mass and escape velocity. Every massive object creates a gravitational pull. If you move slowly enough, you remain bound to it. If you move fast enough, you escape. The same principle applies to galaxies in the local group. If a galaxy's speed relative to the group's center of mass is low enough, it remains bound. If it exceeds the escape velocity, it drifts away. Calculating escape velocity requires knowing the total mass of the system, and here the numbers become even more extraordinary. The local group's total mass is estimated to be on the order of 2 to 3 trillion times the mass of the Sun. Most of that mass is not in stars but in dark matter. Dark matter does not emit light, but it dominates gravity. The Milky Way's visible stars account for only a small fraction of its total mass. Surrounding the luminous disk is a vast halo of dark matter extending far beyond what can be seen. Andromeda has its own dark matter halo. These halos overlap, forming a shared gravitational envelope that binds the local group together. Imagine 2 enormous invisible spheres overlapping in space, each one containing the stars we see. The overlap region is filled with dark matter from both halos, strengthening the gravitational bond between the galaxies. This invisible structure defines the group's true scale more than the visible disks do. Light years give us distance, but gravity gives us structure. Without gravity, the millions of light years between galaxies would represent isolation. With gravity, they represent connection. Even so, those connections are incredibly delicate. The gravitational pull between the Milky Way and Andromeda is strong enough to draw them together over billions of years, but it is not a rapid force. Their approach is slow, measured in tens of kilometers per second relative to each other, modest compared to cosmic speeds. This slowness emphasizes how vast the distances are. If Andromeda is moving toward us at roughly 100 kilometers per second, and it is 2.5 million light-years away, the merger will take billions of years to complete. Gravity works steadily, but space is immense. Another way to grasp scale is to compress it. If the Milky Way were reduced to the size of a coin, Andromeda would be another coin several meters away. The dwarf galaxies would be tiny specks scattered across a large room, and the room itself would represent millions of light-years of mostly empty space. That emptiness is part of the scale. The local group is not densely packed. Its galaxies occupy a tiny fraction of its total volume. Most of the space between them contains extremely thin gas and dark matter, with densities far lower than any vacuum humans can create. Yet that thin matter matters. The intergalactic medium within the local group carries mass, contributes to gravity, and may influence how galaxies evolve. Though invisible to the eye, it is part of the structure that binds the system. When astronomers talk about the size of the local group, they often refer to the zero-velocity surface. This is the distance from the group's centre of mass at which the inward pull of gravity balances the outward push of cosmic expansion. Inside this surface, galaxies are gravitationally bound. Outside it, they join the expanding universe. Estimates place this boundary at roughly 3 to 4 million light-years from the centre of mass. That means the diameter of the bound region is on the order of 6 to 8 million light-years. Some definitions extend even farther, depending on which galaxies are included. The boundary is not a wall, it is a transition zone. Galaxies near it move slowly relative to the group, and small measurement errors can change whether they are considered members. But conceptually, it gives a sense of where gravity's dominance ends. Scale also operates in time. Light years remind us that when we observe distant galaxies, we see them as they were in the past. Within the local group, those time differences are small compared to cosmic history, but they are still meaningful. Observing triangulum means seeing it 3 million years ago. Observing Andromeda means looking even farther back. These time delays are tiny compared to the billions of years over which galaxies evolve, but they add depth to our understanding. The local group is not just large in space, it stretches backward in time as well, with each observation a glimpse into a slightly different era. All of this leads back to the central question of scale. How big is the local group? In linear terms, several million light-years across. In mass, several trillion suns. In time, billions of years of shared evolution. In emptiness, vast beyond ordinary comprehension. And yet, within this enormous structure, gravity provides coherence. It creates a shared fate. The Milky Way, Andromeda, Triangulum, and dozens of dwarf galaxies are not drifting independently. They are bound together, moving slowly through space as a single gravitational entity. Light years stretch the imagination outward. Gravity pulls it back together. One measures separation, the other ensures connection. Between them lies the true scale of the local group. If there is a boundary, however soft, where does it lie? And what happens just beyond it, where the local group's grip loosens and the broader universe takes over? At some point when talking about a structure as large and diffuse as the local group, the question almost asks itself, if this is a group, if these galaxies belong together, then where does that belonging stop? Where does the local group actually end? The moment you ask this, you run into an uncomfortable truth. There is no clear edge, no cosmic fence, no visible line in space where one structure hands things over to the next. Instead, the boundary of the local group is defined by balance, motion and influence, all of which fade gradually rather than stopping outright. From Earth, it is tempting to imagine astronomical structures as objects with shapes and outlines. Galaxies look like disks or ellipses. Nebulae look like clouds. Even galaxy clusters can appear as dense knots of light. But the local group is not something you can point to in a photograph and say, that's where it ends. It is more like a region where gravity still has the final word. The most widely used concept for describing the local group's boundary is something called the zero-velocity surface. The name sounds technical, but the idea behind it is fairly intuitive. It refers to the distance from the group's centre of mass at which the inward pull of gravity exactly balances the outward push of cosmic expansion. Inside this surface, galaxies are gravitationally bound. Outside it, the expansion of the universe wins and galaxies drift away, never to return. This balance point is not fixed in the way a physical surface is fixed. It depends on the total mass of the local group and on the expansion rate of the universe. Both of these quantities are known only within certain margins of uncertainty. As measurements improve, estimates of the boundary shift slightly. The edge of the local group is therefore best thought of as a zone rather than a line. Current estimates place the radius of this gravitationally bound region at roughly 3 to 4 million light-years from the local group's centre of mass. That centre is not located inside the Milky Way. It lies somewhere between the Milky Way and Andromeda, closer to Andromeda because it is slightly more massive. From that point, gravity reaches outward in all directions, weakening gradually with distance. If you imagine standing at the centre of the local group and moving outward, the change would be subtle. Galaxies closer in would move in complex orbits, influenced by the pull of the major members. Farther out, motions would slow relative to the group's centre. Eventually, at the zero-velocity surface, a galaxy would appear almost stationary with respect to the group, neither clearly falling inward nor clearly drifting away. Beyond that surface, galaxies begin to participate more fully in the expansion of the universe. Their motion is no longer dominated by the local group's gravity. Space itself carries them outward, increasing their separation over time. Once a galaxy crosses this boundary, it is effectively lost to the group forever. What makes this boundary difficult to visualize is that it does not look like anything. There is no change in brightness, no drop-off in star density that clearly marks it. The local group does not fade out in a visible way. Instead, astronomers infer its boundary by studying the motion of galaxies near the edge and asking a simple question: are they bound or not? This question turns out to be surprisingly hard to answer. Measuring a galaxy's distance is challenging. Measuring its velocity accurately is also challenging. Small uncertainties in either can change the conclusion. A galaxy might appear to be a member in one study and an outsider in another. Some galaxies occupy this ambiguous region. They sit near the estimated boundary, moving slowly relative to the local group, with velocities that could be consistent with either being bound or drifting away. These galaxies are often described as borderline members. Their existence reinforces the idea that the local group's edge is fuzzy rather than sharp. Another complication comes from the fact that gravity does not operate in isolation. The local group is not floating alone in space. It is part of a much larger cosmic environment. Nearby galaxy groups exert their own gravitational influence. Large-scale structures tug gently on everything around them. The local group's boundary is shaped not only by its own mass, but also by the surrounding universe. In some directions, the local group's influence may extend slightly farther. In others, it may be truncated by the pull of neighbouring structures. This gives the group an irregular, somewhat elongated shape rather than a neat sphere. Its boundary bulges and dips depending on the distribution of mass beyond it. The galaxies near the edge often reveal this complexity. Their motions do not always point neatly toward the local group's centre. Some show signs of being pulled in multiple directions at once. Their paths through space reflect a competition between gravitational influences on different scales. When astronomers talk about the local group ending, they are therefore speaking in statistical terms. They are describing the region where, on average, gravity from the group no longer dominates motion. This is a useful definition, but it is not absolute. There is also a conceptual distinction between the local group's gravitational boundary and its observational boundary. Observationally, the local group includes galaxies that are close enough and slow enough to be studied in detail. Practically speaking, astronomers can map this region with relative precision compared to more distant structures. But observational convenience does not define physical reality. The local group's influence may extend farther than the most distant galaxy we can currently associate with it. There may be faint dwarf galaxies beyond the known members that remain bound but undetected. Each new discovery has the potential to nudge the boundary outward. This uncertainty means that the size of the local group is not a single number. It is a range. Depending on how strictly membership is defined, the group might be said to span 6 million light-years, 8 million, or even more. None of these figures is wrong. They reflect different ways of drawing the line. Another way to think about where the local group ends is to consider time. Gravity does not act instantaneously across millions of light-years. Changes in mass distribution propagate at the speed of light. The local group we observe today reflects gravitational relationships established billions of years ago. Some galaxies near the edge may be in the process of leaving. They may have been bound in the past, but are now slowly crossing the threshold where expansion takes over. Others may be falling in for the first time, captured by the group's gravity as the universe evolves. This dynamic picture means that the local group's boundary is not static. It changes over time. Early in the universe, when galaxies were closer together, the local group's region of influence may have been different. In the far future, as cosmic expansion accelerates, the group may become more isolated, its boundary shrinking in relative terms as distant galaxies recede beyond reach. From a human perspective, these changes are imperceptibly slow. Over a lifetime, the local group's boundary does not move in any meaningful way. But over billions of years, the structure evolves. The concept of an ending also depends on what you consider the local group to be. If you think of it as a collection of visible galaxies, the group ends where those galaxies stop. If you think of it as a gravitational structure dominated by dark matter, the group extends much farther than what we can see. Dark matter halos do not have sharp edges. Their density decreases gradually with distance. The dark matter associated with the local group likely blends into the larger dark matter filaments of the cosmic web. In this sense, the local group fades into the universe rather than ending cleanly. This blending challenges the idea of discrete cosmic objects. On large scales, the universe is continuous. Structures overlap, merge, and dissolve into one another. The local group is a recognizable feature within this continuity, but it is not isolated in the way a planet or a star is isolated. There is also a psychological aspect to the question of where the local group ends. Humans prefer boundaries. They help us organize information and make sense of complexity. Saying this belongs here and that belongs there is comforting. The universe does not always cooperate with that preference. Accepting that the local group has a soft edge rather than a hard one requires a shift in thinking. It means embracing gradients rather than borders, influence rather than ownership, membership rather than containment. This way of thinking aligns with how gravity actually works. Gravitational influence decreases with distance, but never truly drops to zero. Even galaxies far beyond the local group feel its pull, however faintly. The question is not whether gravity exists, but whether it matters enough to shape motion. At some distance, the answer becomes no. Beyond the local group's boundary, galaxies are effectively free from its influence. They follow the broader flow of the universe, moving along with cosmic expansion and responding to larger structures instead. This transition is gradual, and that gradualness is the key to understanding the group's true size. The local group is not a bubble carved out of space. It is a region where one influence happens to dominate. Seen this way, the question, where does the local group end, becomes less about finding an edge and more about understanding relationships. Which galaxies are bound to one another? Which share a common future? Which are drifting away? The galaxies inside the local group are tied together by gravity. Their futures are linked. The Milky Way and Andromeda will merge. Dwarf galaxies will be absorbed. The group will become more compact over time. Galaxies outside the group do not share this fate. They will continue to recede, eventually disappearing beyond the observable horizon as space expands. From the perspective of the distant future, the local group may become the only structure visible, an isolated island of galaxies surrounded by darkness. That future isolation gives the local group's boundary an added significance. It marks the region of the universe that will remain accessible, both physically and observationally in the very long term. Everything beyond it will slip away. Right now, though, the boundary remains a matter of careful measurement and interpretation. Astronomers refine it by studying velocities, distances, and mass distributions. Each improvement sharpens the picture slightly, even as the edge remains soft. Understanding where the local group ends also prepares us for looking beyond it. Once we know where its influence fades, we can begin to explore what lies just outside. Neighbouring groups, larger structures, the broader cosmic web. The local group is not the end of structure, but it is the end of our immediate gravitational neighbourhood. Beyond it lies a different regime, governed by larger scale dynamics and shaped by structures far bigger than our local collection of galaxies. If the local group were made only of what we can see, it would not exist as a stable structure at all. The distances are too large, the visible matter is too sparse, the motions of galaxies would not make sense. Something unseen must be at work, quietly shaping the system, holding it together across millions of light years. That unseen component is dark matter, and without it the local group would unravel. Dark matter is not a small correction to the picture. It is the dominant ingredient. In the Milky Way, stars, gas and dust make up only a small fraction of the total mass. The rest is invisible. The same is true for Andromeda, for triangulum, and for the dwarf galaxies scattered throughout the local group. When astronomers talk about the mass that binds the group together, they are talking mostly about dark matter. The idea that something invisible could outweigh everything we see did not come easily. It emerged slowly, out of careful measurements that refused to agree with expectations. One of the earliest clues came from the way galaxies rotate. If all the mass of a galaxy were concentrated in its visible stars, stars farther from the centre should orbit more slowly, much like planets in the outer solar system move more slowly than those closer to the Sun. But when astronomers measured the rotation of galaxies, they found something strange. The outer stars were moving just as fast as those nearer the centre. This behaviour could not be explained by visible matter alone. There simply was not enough mass in stars and gas to keep those fast-moving outer stars bound. Either gravity behaved differently on large scales, or there was additional mass that could not be seen. Over time, evidence from many different observations pointed to the same conclusion. There was extra mass, and it was dark. In the context of the local group, dark matter does more than shape individual galaxies. It creates the shared gravitational environment that makes the group a group. Each major galaxy is embedded in its own dark matter halo, an enormous, roughly spherical distribution of mass extending far beyond the visible stars. These halos overlap and interact, forming a larger structure that encompasses the entire local group. The Milky Way's dark matter halo likely extends several 100,000 light-years from the galactic centre. Andromeda's halo is even larger. Between them lies a region where these halos overlap, increasing the gravitational pull and strengthening the bond between the two galaxies. This overlapping region is a key reason the Milky Way and Andromeda are moving toward each other rather than drifting apart. Triangulum, too, is embedded in its own dark matter halo, though smaller. Its halo interacts primarily with Andromeda's, reinforcing the idea that Triangulum is likely bound to Andromeda within the local group's hierarchy. The dwarf galaxies scattered throughout the group each carry their own dark matter halos as well, tiny but dense, often containing far more dark matter than visible stars. When astronomers calculate the total mass of the local group, they rely heavily on the motions of galaxies relative to one another. By measuring how fast galaxies are moving and how far apart they are, scientists can estimate how much mass must be present to keep them bound. Time and again, these calculations yield values far higher than what visible matter alone can account for. The result is striking. The local group's total mass is estimated to be on the order of 2 to 3 trillion times the mass of the Sun. Of that, roughly 80 to 90% is dark matter. The stars, gas and dust that capture our attention are the minority component, floating within a much larger invisible structure. This invisible structure determines the local group's size in a very real sense. The reach of gravity depends on mass. Because dark matter contributes most of the mass, it sets the scale of the gravitational boundary. Without dark matter, the zero-velocity surface would be much closer in. Many galaxies currently considered members would not be bound at all. Dark matter also explains why the local group is relatively stable, despite the expansion of the universe. Cosmic expansion pulls galaxies apart, but gravity pulls them together. The balance between these two effects depends on mass. The more mass present, the stronger gravity becomes. Dark matter tips that balance in favour of cohesion. Another important role of dark matter lies in the formation of the local group itself. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly with tiny fluctuations in density. Dark matter clumped first, forming gravitational wells that attracted ordinary matter. Gas fell into these wells, cooling and forming stars and galaxies. The local group likely formed around a region of enhanced dark matter density. As dark matter clumped, it drew in gas and smaller structures, gradually assembling the galaxies we see today. The Milky Way, Andromeda, and triangulum grew within this shared environment, their histories shaped by the underlying dark matter distribution. This means that dark matter is not just holding the local group together now, it has been shaping it from the very beginning. The arrangement of galaxies, their motions and their future interactions are all influenced by how dark matter is distributed on these scales. Dwarf galaxies offer particularly strong evidence for dark matter's role. Many of them have very little visible matter. Some contain only a few thousand stars, yet those stars move in ways that imply the presence of substantial mass. In some cases, the ratio of dark matter to visible matter is hundreds to 1. These extreme ratios make dwarf galaxies sensitive probes of dark matter. If dark matter behaved differently than expected, or if alternative theories of gravity were correct, these systems would reveal discrepancies. So far, their behavior aligns well with the presence of dark matter. The distribution of dwarf galaxies within the local group also reflects the structure of the dark matter halo. They are not randomly scattered. They tend to cluster around the major galaxies, tracing regions of higher dark matter density. Some appear to lie along preferred planes or streams, hinting at the complex ways dark matter and galaxy formation interact. Dark matter also influences how the local group will evolve in the future. As the Milky Way and Andromeda draw closer, their dark matter halos will merge first, long before the visible disks collide. This merger will deepen the gravitational well at the group's centre, drawing in smaller galaxies and reshaping the system. During the eventual merger, dark matter will dominate the dynamics. The visible stars will largely pass through one another, but the dark matter halos will interact strongly, redistributing mass and energy. The resulting galaxy will be surrounded by a new, larger halo, altering the group's structure permanently. The invisibility of dark matter makes it tempting to treat it as an abstract concept, but its effects are concrete. Without it, the local group would not have its current size, shape, or stability. The distances between galaxies would not correspond to their motions. The future merger of the Milky Way and Andromeda would not occur. There is also an important subtlety. Dark matter does not interact with itself, or with ordinary matter, in the same way ordinary matter does. It does not collide, stick, or radiate energy. This collisionless nature allows dark matter halos to extend smoothly and overlap without friction. It also means dark matter structures are diffuse rather than sharply bounded. This diffuseness contributes to the local group's soft edges. Because dark matter halos fade gradually with distance, the group's gravitational influence fades gradually as well. There is no sharp cut-off where dark matter suddenly ends. Instead, its density decreases, blending into the larger cosmic web. That blending connects the local group to the wider universe. The group's dark matter halo is part of a filamentary network, stretching across hundreds of millions of light years. These filaments connect galaxy groups and clusters, forming the large-scale structure of the cosmos. The local group is a node within this network, not an isolated island. Understanding dark matter also reframes how we think about scale. When we picture the local group, we often imagine the visible galaxies floating in space. A more accurate picture would place those galaxies inside overlapping, translucent spheres of dark matter, filling a much larger volume than the stars alone suggest. This perspective changes how big the local group feels. Its visible members may span several million light-years, but its dark matter environment extends farther, influencing motion and structure beyond what we can directly observe. In this sense, the local group is larger than it appears. The challenge, of course, is that dark matter remains mysterious. We know it exists because of its gravitational effects, but we do not yet know what it is made of. Numerous experiments are underway to detect dark matter particles directly or indirectly, but so far the results remain inconclusive. Despite this uncertainty, dark matter's role in the local group is well established. Any viable theory of cosmic structure must account for it. Without dark matter, the observed motions and distributions of galaxies simply do not add up. From a practical standpoint, dark matter allows astronomers to make sense of the local group's boundaries. By modelling the distribution of dark matter, scientists can estimate where gravity dominates and where expansion takes over. These models help define the group's size in a physically meaningful way. Dark matter also helps explain why the local group is relatively isolated. Its mass is sufficient to bind its members, but not so large as to pull in distant galaxy groups. This balance places the local group in a middle ground, neither a small, fragile association nor a massive cluster. The invisibility of dark matter gives it an almost poetic quality, but it's important to keep the language grounded. Dark matter is not mystical. It is a component of the universe that behaves according to physical laws, even if those laws are not yet fully understood. Its effects are measurable, predictable, and essential. When thinking about the local group, it helps to imagine dark matter as the scaffolding on which everything else is built. The stars, gas, and galaxies are the visible decorations. Remove the scaffolding, and the structure collapses. Even though the local group feels vast and stable when described in terms of size and mass, it is not sitting still. Nothing in the universe truly is. Every galaxy, every group, every cluster is in motion, carried along by gravity, expansion, and the accumulated influence of structures far beyond what we can see directly. The local group is no exception. It is drifting through space, slowly and steadily, its members moving in complex patterns that reveal both where the group has been and where it is going. From inside the Milky Way, this motion is impossible to sense directly. There is no wind, no vibration, no shift in the stars overhead that would hint at movement. And yet, measurements show that our entire galactic neighbourhood is travelling through space at hundreds of kilometres per second. This motion does not contradict the expansion of the universe. It exists on top of it, layered and intertwined. To understand how the local group moves, it helps to separate different kinds of motion. First, there is the internal motion of galaxies within the group. The Milky Way, Andromeda, triangulum, and the dwarf galaxies are all moving relative to one another, orbiting a shared centre of mass. This motion defines the group as a gravitationally bound system. Then, there is the motion of the local group as a whole, drifting relative to the rest of the universe. This is sometimes called peculiar velocity, meaning motion that deviates from the smooth expansion of space. This peculiar velocity arises because gravity pulls on the local group from nearby concentrations of mass. Finally, there is cosmic expansion itself, which increases the distance between structures that are not gravitationally bound. The local group participates in expansion on very large scales, but internally, gravity dominates. Inside the local group, motion is slow and deliberate. Galaxies do not whip around each other like planets around a star. The distances are too large and the gravitational pull too gentle for that. Instead, orbits stretch over billions of years. A single loop around the group's centre of mass can take longer than complex life has existed on Earth. The most important internal motion is the one between the Milky Way and Andromeda. These two galaxies are moving toward each other at roughly 100 kilometers per second. That speed is measured by observing the Doppler shift of Andromeda's light. The light is slightly blue-shifted, indicating motion toward us rather than away. This inward motion tells astronomers that the local group is not expanding internally. The Milky Way and Andromeda are bound. Their mutual gravity overwhelms cosmic expansion at this scale. Over billions of years, this approach will culminate in a merger, reshaping the group's structure. Triangulum's motion adds another layer of complexity. Its velocity suggests that it is likely bound to Andromeda, rather than moving freely between the two giants. Its orbit may be elongated and tilted, taking it far from Andromeda at some points and closer at others. This motion contributes to the overall gravitational dance within the group. Dwarf galaxies exhibit a wide range of motions. Some orbit close to the Milky Way, moving in elongated paths that carry them through the galactic halo. Others orbit Andromeda. A few move through the space between, responding to the combined pull of both major galaxies. By measuring these motions, astronomers can infer the total mass of the local group. Faster motions imply stronger gravity, and therefore more mass. The observed velocities consistently indicate that dark matter dominates the system, shaping how everything moves. Internal motion also reveals the group's shape. The distribution of velocities suggests that the local group is not spherical. Instead, it appears somewhat elongated, with motion preferentially aligned along the axis connecting the Milky Way and Andromeda. This elongation reflects how the group formed and how mass is distributed within it. Beyond internal motion lies the movement of the local group as a whole. Relative to the cosmic microwave background, which serves as a reference frame for the universe's expansion, the local group is moving at roughly 600 kilometers per second. This motion is not random. It is directed toward a region of space with a high concentration of mass. This region lies in the general direction of the Virgo cluster and other nearby large-scale structures. Their combined gravitational pull tugs on the local group, drawing it along. This pull does not disrupt the group's internal cohesion, but it does determine the direction in which the group drifts through space. This drifting motion has been measured by observing the dipole anisotropy in the cosmic microwave background. In one direction, the background radiation appears slightly hotter, indicating motion toward it. In the opposite direction, it appears slightly cooler. This pattern reveals the local group's velocity relative to the universe's average expansion. The idea that the local group is moving through space can feel counterintuitive. After all, space itself is expanding. How can something move through something that is stretching everywhere? The answer lies in scale. On the larger scales, expansion dominates. On smaller scales, gravity creates deviations from that expansion. Think of space as a slowly expanding surface with small ripples and currents. The local group sits on that surface, carried outward by expansion, but also sliding sideways due to gravitational pulls from nearby mass concentrations. Its motion is the vector sum of these influences. This motion matters for several reasons. It affects how we measure distances and velocities. It shapes the local group's long-term future, and it connects our local environment to the broader cosmic web. One subtle consequence of motion is the distortion of velocity measurements. When astronomers measure the redshift or blueshift of nearby galaxies, they must account for the local group's own motion. Without this correction, distance estimates and membership classifications would be skewed. Motion also affects how the local group interacts with its surroundings. As it drifts, it encounters regions of slightly different dark matter density. Over extremely long timescales, this could influence how the group evolves, though the effects are gentle rather than dramatic. The local group's motion also reflects its history. The direction and speed of drift encode information about past interactions and the distribution of matter nearby. By reconstructing these motions, astronomers can infer how the group formed and how it has moved through the universe over billions of years. Internal motion within the group is also tied to energy exchange. As galaxies interact gravitationally, energy is redistributed. Some galaxies lose energy and sink toward the centre. Others gain energy and move outward. Over time, this process leads to a more compact configuration. This is one reason the local group is expected to become more tightly bound in the future. As the Milky Way and Andromeda merge, the group's internal motions will reorganize. Dwarf galaxies may be drawn inward or flung outward, depending on how energy is transferred during interactions. The motion of stars within galaxies also contributes to the overall picture. Stars orbit galactic centers, gas clouds swirl, dark matter particles move through halos. These smaller scale motions average out on group scales, but they are part of the same gravitational framework. Another important aspect of motion is time scale. The velocities involved may sound large, hundreds of kilometers per second, but when spread over millions of light years, the resulting changes are slow. Over 1 million years, the local group moves only a small fraction of its own size. This slowness can be comforting. It means the structure we see today will remain recognizable for a long time. The night sky will not change abruptly. The local group's arrangement evolves on timescales far beyond human experience. At the same time, this slow motion ensures that change is inevitable. Over billions of years, the group's internal configuration will shift dramatically. The Milky Way and Andromeda will merge. Triangulum will likely be absorbed. Smaller galaxies will be incorporated or scattered. Motion also determines what the local group will eventually see. As the universe's expansion accelerates due to dark energy, distant galaxies will recede faster and faster. Over time, they will slip beyond the observable horizon. The local group's peculiar motion will become less relevant compared to this acceleration. In the far future, the local group may appear isolated, surrounded by darkness, its members the only galaxies visible. In that scenario, motion within the group will dominate all observable dynamics. Everything beyond will have moved too far away to be detected. This future isolation gives present-day motion a sense of context. Right now, the local group is part of a rich cosmic environment, influenced by neighbouring structures. In the distant future, it may become a closed system, its motion defined entirely by internal gravity. Understanding the local group in motion also helps clarify the concept of scale. Size alone does not define a structure. How it moves, how it responds to forces, and how it evolves over time are equally important. Motion reveals connections that static pictures miss. The local group's drift through space is gentle but persistent. It ties our local environment to the broader universe. It reminds us that even structures millions of light years across are not fixed, but part of a larger flow. From where you are now, that motion is abstract. The room is still. The earth feels solid, but beneath that stillness lies a cascade of movement. The planet rotates. It orbits the sun. The sun orbits the centre of the Milky Way. The Milky Way moves toward Andromeda. The local group drifts through space, all of it layered, all of it real. This layered motion is what allows astronomers to trace structure on every scale. By understanding how the local group moves, they can infer what surrounds it, how massive it is, and how it fits into the universe at large. This motion naturally leads to another question. if the local group is drifting, what lies ahead of it? Which structures exert the strongest pull? And how does our local system fit into even larger arrangements of galaxies that stretch far beyond our immediate neighbourhood? Among all the motions unfolding within the local group, one stands out as both deeply significant and strangely calm. The Milky Way is moving toward Andromeda, not rushing, not colliding yet, just approaching steadily, patiently, across a distance so vast that even this approach takes billions of years to complete. It is one of the clearest demonstrations that the local group is a bound system, and it offers a concrete way to understand just how large and how connected this region of space really is. This motion was not always obvious. For a long time, Andromeda was simply a faint patch in the sky, its true nature unknown. Once astronomers realised it was a separate galaxy far beyond the Milky Way, the next question became how it was moving. The answer came from careful measurements of its light. When light from an object is shifted slightly toward the blue end of the spectrum, it means the object is moving toward us. When it shifts toward red, the object is moving away. In the case of Andromeda, the shift is toward blue. This is unusual. Most galaxies show redshift because the universe is expanding and carrying them away from us. Andromeda is one of the very few large galaxies whose light is blue shifted. That alone tells us something important. Andromeda is not participating in the general expansion of the universe relative to us. Its motion is dominated by gravity. The measured approach speed is about 100 kilometers per second. That sounds fast in everyday terms. It is faster than a jet aircraft, faster than a rifle bullet. But across intergalactic distances, it is almost gentle. At that speed, covering the 2.5 million light-years between the Milky Way and Andromeda takes several billion years. This slow approach reveals something fundamental about the scale of the local group. Gravity can only pull galaxies together over such distances if there is an enormous amount of mass involved. The fact that the Milky Way and Andromeda are moving toward each other tells astronomers that the combined mass of the local group is large enough to overcome cosmic expansion on these scales. If the local group were less massive, Andromeda would be drifting away from us like most other galaxies. The expansion of space would dominate. The fact that it does not means we are inside a region where gravity has the upper hand. The approach is not head-on in the simple sense. Andromeda is not moving directly along a straight line toward the centre of the Milky Way. Its motion has both radial and tangential components. The radial component brings it closer. The tangential component gives it sideways motion. Determining the balance between these components has been a major observational challenge. For many years, astronomers could measure only the radial component of Andromeda's motion, the part along our line of sight. Measuring sideways motion across the sky requires extremely precise observations over long periods of time. Eventually, space-based telescopes made it possible to detect this subtle, proper motion. Those measurements suggest that Andromeda's sideways motion is relatively small. This implies that the encounter between the Milky Way and Andromeda is likely to be a direct merger rather than a near miss. But even a direct merger does not mean a sudden crash. It means a prolonged interaction lasting billions of years. Understanding this approach also requires understanding where it comes from. The Milky Way and Andromeda formed relatively close together in the early universe. As dark matter clumped, these galaxies grew within the same region of enhanced density. Their mutual gravity has been shaping their motion ever since. Early on, cosmic expansion carried them apart slightly. But as their masses grew, gravity began to slow that separation. Eventually, expansion was overcome, and the two galaxies began falling back toward each other. This turnaround point is one of the defining features of the local group. The fact that the Milky Way and Andromeda reached this turnaround tells us that the local group's mass is not just large, but sufficiently concentrated. The dark matter halos surrounding both galaxies play a crucial role here. These halos extend far beyond the visible disks and overlap in the space between them. In that overlapping region, dark matter density is higher increasing gravitational attraction. This overlap is one reason the approach is so steady and inevitable. Even before the visible parts of the galaxies interact, their dark matter halos are already influencing each other. This invisible interaction has consequences long before the galaxies themselves touch. As the halos overlap, they exchange energy and momentum. This process, known as dynamical friction, gradually slows the relative motion of the galaxies and causes them to sink toward each other more efficiently. Dynamical friction is subtle but powerful. It arises because a massive object moving through a sea of particles, in this case dark matter, creates a wake behind it. That wake exerts a gravitational pull back on the object, draining its orbital energy. Over time, this effect causes large galaxies to spiral inward toward one another. The Milky Way and Andromeda are already experiencing this process. Their future merger is not a sudden event triggered at the last moment. It is the result of billions of years of gradual energy loss through interactions with dark matter. The approach also affects the smaller galaxies in the local group. Dwarf galaxies respond to the changing gravitational field as the two giants draw closer. Some may be pulled into new orbits. Others may be stripped from one galaxy's influence and captured by the other. A few may be flung outward with increased velocity. These changes will unfold slowly, but they will reshape the local group's internal structure. Over time, the distinction between Milky Way satellites and Andromeda satellites will blur. Separated by millions of light years can still be gravitationally connected strongly enough to reverse cosmic expansion locally. That connection defines the group's identity more clearly than any static boundary. It also highlights the difference between local motion and universal expansion. On scales larger than galaxy groups, expansion dominates. On the scale of the local group, gravity dominates. The Milky Way and Andromeda are close enough and massive enough to resist being carried apart. This balance between expansion and gravity is one of the reasons the local group is such a valuable laboratory for understanding cosmic structure. It sits at the threshold where these two influences compete. By studying systems like ours, astronomers learn how structure forms and persists in an expanding universe. The approach toward Andromeda also carries a time dimension that is easy to underestimate. Billions of years lie between now and the final merger. Over that time, stars will continue to form and die. Planets will orbit. Civilizations may rise and fall. From a human perspective, the approach is effectively static. And yet, from a cosmic perspective, it is already well underway. The distance between the Milky Way and Andromeda is shrinking. The dark matter halos are interacting. The local group's future is being shaped moment by moment. This long time scale also means that the local group is not a permanent arrangement in its current form. The group we describe today is a snapshot. In the far future, it will look very different. The Milky Way and Andromeda will no longer be separate. Triangulum may have merged as well. The group may consist of a single massive galaxy, surrounded by remnants of smaller ones. That future configuration will still be the local group, but its internal distances will be much smaller. Its size, defined by gravitational influence, may shrink even as its mass remains similar. The concept of how big the local group is will change over time. The approach toward Andromeda also has implications for how we understand membership. Galaxies that are currently bound may be absorbed. Others near the edge may drift away as the group's mass distribution changes. The boundary discussed earlier will evolve. All of this reinforces the idea that size in astronomy is not static. It is dynamic, shaped by motion, interaction, and time. The local group is large not just because of its current extent, but because of the gravitational relationships that tie its members together across those distances. From a calmer perspective, there is something grounding about this approach. The universe is not only expanding and dispersing. In some places, things are coming together. Gravity creates islands of connection in an otherwise stretching cosmos. The Milky Way's slow journey toward Andromeda is one of those connections made visible. It turns abstract numbers into a story of motion and eventual union. It reminds us that even on the largest scales we can meaningfully discuss, relationships matter. As this approach continues, it sets the stage for what will eventually be one of the most dramatic transformations in our local universe. Not a sudden catastrophe, but a slow, sweeping reorganization of stars, gas, and dark matter. If the Milky Way and Andromeda are moving toward one another now, what exactly will happen when they finally meet, and how will that reshape the local group as a whole? When people hear the phrase galactic collision, it often conjures images of sudden destruction, stars crashing into one another, worlds flung violently into darkness. It sounds fast, loud, and catastrophic. The reality could not be more different. What awaits the Milky Way and Andromeda is not a crash in the everyday sense, but a slow, drawn-out gravitational dance, unfolding over billions of years, guided more by patience than by violence. This future encounter is one of the clearest ways to understand how large the local group truly is, because it shows how gravity can act across enormous distances and timescales without ever rushing. The story of this future merger begins long before the galaxies visibly interact. In fact, it has already begun. The Milky Way and Andromeda are still separated by roughly 2.5 million light-years, but their dark matter halos have already started to overlap. This means that, long before any stars or gas clouds come close, the invisible mass surrounding both galaxies is already exchanging energy and momentum. This early phase is almost entirely hidden from view. There are no dramatic flares of light, no obvious distortions in the night sky. Yet it is during this phase that the fate of both galaxies is sealed. As their dark matter halos interpenetrate, dynamical friction steadily drains orbital energy from the system. This process is slow but relentless. It ensures that the galaxies cannot simply swing past one another and escape. Over time, their relative motion becomes more inward, less sideways, drawing them ever closer. Several billion years from now, the first close approach will occur. By that point, the galaxies will be much nearer than they are today, and their mutual gravity will begin to noticeably distort their shapes. Spiral arms will stretch and warp. Long tidal tails of stars and gas will be pulled outward, arcing through space like luminous streamers. These features will be enormous, spanning hundreds of thousands of light years, yet they will form gradually, not suddenly. Even at this stage, individual stars will almost never collide. The distances between stars are so vast that direct impacts are extraordinarily unlikely. Galaxies are mostly empty space. When they pass through one another, their stars behave more like ghostly swarms than solid objects. They interweave, responding to gravity rather than physical contact. Gas clouds, however, are a different matter. When the galaxy's interstellar gas begins to interact, compression and shock waves will occur. This will trigger bursts of star formation. Regions that are relatively quiet today may blaze with new stars in the distant future. The merged system will likely experience periods of intense stellar birth, lighting up regions that are currently dark. After the first close pass, the galaxies will separate again, but not by much. They will arc outward, slowed by the energy they have lost. Their shapes will already be changed, their disks less orderly, their spiral patterns disrupted. Over time, gravity will pull them back together for another pass, closer than the first. This back-and-forth motion may repeat several times. Each pass strips more energy from the system, tightens the orbit, and deepens the merger. The entire process may take several billion years from first encounter to final coalescence. From a human perspective, it is unimaginably slow. From a cosmic perspective, it is perfectly ordinary. Eventually, the Milky Way and Andromeda will settle into a single gravitational center. Their stars will redistribute into a new configuration, likely forming a large elliptical galaxy rather than a spiral. The familiar disk structure of the Milky Way will be gone, replaced by a more rounded, diffuse distribution of stars. This outcome is not unusual. Many large elliptical galaxies in the universe are thought to be the result of past mergers between spiral galaxies. The local group is simply following a well-worn cosmic path, one that plays out over immense distances and times. The Sun, if it still exists by then, will not be at the centre of the action. It will be carried along with the Milky Way's stars, possibly flung into a more distant orbit around the merged galaxy's centre, or perhaps drawn closer inward. Predicting its exact fate is difficult, but one thing is clear. Earth will not be destroyed by a direct stellar collision. Any changes would come from long-term shifts in radiation, gravitational environment, or stellar neighbourhood. By the time of the final merger, however, the Sun will be much older. Billions of years from now, it will have left the main sequence or be nearing that transition. Life on Earth, if it exists at all, will be facing challenges unrelated to galactic dynamics. The merger will be a backdrop to much larger changes in the solar system itself. While the Milky Way and Andromeda are the main participants in this dance, they are not alone on the floor. Triangulum will almost certainly be involved as well. Depending on its orbit, it may merge with Andromeda before the main collision, or it may be drawn into the combined system afterward. Either way, it will contribute stars, gas, and dark matter to the final structure. The dwarf galaxies of the local group will also be affected. As the two giants merge, their combined gravitational field will deepen. Some dwarf galaxies will be drawn inward and absorbed. Others may be flung outward, gaining energy during close encounters and moving on to wider orbits. The population of satellites will be reshuffled. This redistribution highlights something important about scale. The local group is not just large in terms of distance, it is large in terms of gravitational reach. Events involving only two galaxies can influence objects millions of light years away. The merger will not be a local disturbance, it will reshape the entire group. Over time, as the merger progresses, the local group will become more compact. Its mass will remain similar, but it will be more centrally concentrated. The zero-velocity surface discussed earlier may shift inward slightly as mass redistributes and cosmic expansion continues to accelerate. The group's effective size will change, not because mass disappears, but because structure reorganizes. This future evolution underscores why the local group cannot be thought of as a static object. Its size is not a fixed measurement etched into space. It is a living quantity, defined by gravitational relationships that evolve over time. The slow nature of this cosmic dance also reveals something subtle about gravity itself. Gravity does not demand immediacy. It works patiently, accumulating small effects over vast timescales. The merger of galaxies separated by millions of light years is not dramatic, because gravity is weak, but because space is enormous. There is also a sense in which this future collision simplifies the local group. Today, the group has multiple major galaxies, dozens of dwarfs, and a complex internal structure. In the distant future, it may be dominated by a single massive galaxy surrounded by remnants. The richness of variety will give way to consolidation. This does not mean the local group will become less interesting. The merged galaxy will carry within it the histories of all its predecessors. Stars formed in different galaxies will coexist in a shared structure, their origins written into their motions and compositions. The local group's past will be preserved in its future form. From an even more distant perspective, this merger will be happening in a universe that is itself changing. Dark energy will continue to accelerate cosmic expansion. Distant galaxies and groups will recede beyond the observable horizon. Eventually, the local group may become the only visible structure in the universe, an island of stars surrounded by darkness. In that scenario, the merger between the Milky Way and Andromeda takes on added significance. It will not just reshape the local group, it will define the entire observable cosmos for whatever observers exist then. Everything beyond the group will be unreachable, invisible, lost to expansion. Seen this way, the slow collision is not an isolated event. It is part of a broader cosmic transition from a connected universe to one of increasing isolation. The local group's future compactness mirrors the universe's future fragmentation on the larger scales. For now, though, this collision remains far away in time. Its importance lies less in its immediate effects and more in what it teaches us about scale. Two galaxies separated by millions of light-years are still close enough, gravitationally, to be bound. The local group is large enough to host such interactions and cohesive enough to guide them. The phrase slow cosmic dance is sometimes used because it captures this combination of motion and patience. The galaxies are not rushing toward an end. They are responding to gravity in the only way gravity knows how, steadily, persistently, without concern for human timescales. Understanding this future dance also helps clarify why the local group is considered a meaningful structure. It is not just a temporary association of galaxies passing by one another. It is a system with a shared future, defined by interactions that are already underway. As we move forward, this shared future raises another question. If the local group will eventually consolidate into a single massive galaxy, how does it compare to larger structures beyond it right now? How does our local system fit into the broader hierarchy of groups, clusters, and superclusters that fill the universe? Once the local group is placed in motion and its future is allowed to unfold, it becomes natural to look outward again and ask what lies beyond this quiet island of galaxies. The local group feels large when measured in millions of light-years and trillions of solar masses. But in the broader structure of the universe, it is only one small gathering among many. Beyond it lie larger collections of galaxies, denser environments, and structures whose scales dwarf even our expansive neighbourhood. One of the nearest and most important of these is the Virgo cluster. The Virgo cluster is not part of the local group. It is something different entirely. It is a massive galaxy cluster containing thousands of galaxies bound together in a much denser gravitational environment. While the local group is spread thinly across space, with large distances separating its members, the Virgo cluster is comparatively crowded. Galaxies there are closer together, interactions are more frequent, and the gravitational field is far stronger. The Virgo cluster lies roughly 50 to 60 million light-years away from the Milky Way. That distance places it well outside the local group's gravitational boundary. Galaxies in Virgo are not bound to us, and we are not bound to them. Yet despite this separation, Virgo plays an important role in shaping the motion of the local group as a whole. When astronomers measure the direction in which the local group is drifting through space, they find that a significant component of that motion points toward the Virgo cluster. This does not mean that we are falling into Virgo in the way that dwarf galaxies fall into the Milky Way. The distance is far too large for that. Instead, Virgo represents a nearby concentration of mass whose gravity tugs gently on everything around it, including us. The Virgo cluster contains a staggering amount of mass. Its total mass is estimated to be on the order of 1 quadrillion times the mass of the Sun. Most of that mass, as with all large cosmic structures, is dark matter. This immense mass creates a deep gravitational well, one that shapes the motion of galaxies across tens of millions of light-years. Compared to Virgo, the local group is small. It contains only a few dozen galaxies rather than thousands. Its total mass is hundreds of times lower. Its internal velocities are slower, its environment quieter. These differences highlight an important point. Not all galaxy groupings are created equal. There is a hierarchy of structure in the universe, with small groups embedded within larger ones, which are themselves embedded within even larger frameworks. The Virgo cluster is part of this hierarchy. It is one of the nearest examples of a rich galaxy cluster, and because of its proximity, it has been studied extensively. Its galaxies come in many forms. Large ellipticals dominate its core, while spirals and irregulars populate its outskirts. This distribution reflects the intense gravitational interactions that occur in dense clusters. In the core of Virgo, galaxies move rapidly. often at speeds of over 1,000 kilometers per second. Close encounters are common. Gas is stripped from galaxies as they move through the hot intracluster medium. Star formation is often suppressed. The environment is harsh compared to the local group's relative calm. This contrast helps explain why the local group looks the way it does. Our region of space is not crowded. It lacks the intense interaction seen in clusters. As a result, the Milky Way has been able to maintain its spiral structure for billions of years. Gas has not been stripped away en masse. Star formation has proceeded in a relatively orderly fashion. If the Milky Way were located in a cluster like Virgo, its history would be very different. Repeated close encounters would have distorted its disk. Gas might have been removed, shutting down star formation long ago. The existence of stable planetary systems, and by extension, life as we know it, might have been far less likely. So while Virgo represents a larger and more massive structure, it also represents a very different environment. The local group's size is not just a matter of distance and mass, it is also a matter of density and interaction rate. In that sense, our local environment is unusually gentle. Beyond the Virgo cluster lie even larger structures. Galaxy clusters themselves are not isolated. They're connected by vast filaments of dark matter and gas, forming what astronomers call the cosmic web. This web stretches across hundreds of millions of light years, linking clusters, groups, and individual galaxies into a continuous network. Within this network, matter is not evenly distributed. Dense nodes host clusters like Virgo. Long filaments connect these nodes. Between them lie vast voids, regions with relatively little matter. The local group resides on the edge of one such filament, in a region of moderate density rather than at a major node. This placement affects how the local group moves and evolves. The gravitational pull from Virgo and other nearby structures draws the local group along the filament. At the same time, the lower density environment limits the number of strong interactions with other groups. When astronomers map the distribution of galaxies on very large scales, they find that the local group is part of a larger structure sometimes called the local sheet. This is a flattened arrangement of galaxies extending tens of millions of light years. The Virgo cluster sits at one end of this sheet, acting as a massive anchor. This sheet-like structure adds another layer to our understanding of scale. The local group is not just floating randomly in space. It is part of an organized pattern shaped by dark matter and cosmic expansion. Its size and motion are influenced by this larger context. The influence of Virgo extends beyond simple attraction. It also helps define what lies beyond the local group. Galaxies on the far side of the group, in the direction opposite Virgo, experience different gravitational conditions. Their motions reflect a balance between the pull of Virgo and the general expansion of the universe. This asymmetry means that the local group's boundary is not the same in all directions. In the direction of Virgo, the gravitational landscape is steeper. In other directions, it is flatter. This contributes to the irregular shape of the local group's gravitational domain. When considering scale, it is useful to think in terms of nesting. The Milky Way is part of the local group. The local group is part of a larger galaxy sheet. That sheet is part of a filament. The filament connects to clusters like Virgo. Virgo itself is part of an even larger supercluster structure. Each level in this hierarchy increases the scale dramatically. The local group spans a few million light years. The Virgo cluster spans several million light years itself, but its influence reaches much farther. The filament connecting them stretches tens of millions of light years. The supercluster encompasses hundreds of millions. At each step, the character of the environment changes. Interactions become more frequent. Velocities increase. The balance between gravity and expansion shifts. The local group occupies a middle ground in this hierarchy. It is large enough to resist expansion internally, but small enough to remain relatively isolated. This middle position has consequences. It allows the local group to be long-lived. Groups like ours can persist for billions of years without being torn apart or absorbed into a larger cluster. Over cosmic time, some groups do fall into clusters, becoming substructures within them. Others remain on the outskirts indefinitely. Whether the local group will ever be absorbed by Virgo is an open question, but current understanding suggests that it is unlikely. The accelerating expansion of the universe, driven by dark energy, is making it harder for gravity to pull distant structures together. While Virgo's gravity influences our motion, it may never fully capture us. This introduces an important distinction. Being influenced by a structure does not mean being bound to it. The local group is influenced by Virgo, but it is not a member of the Virgo cluster. The difference lies in whether gravity can overcome expansion over the relevant distance. This distinction helps clarify how astronomers think about cosmic neighborhoods. The local group is our immediate neighborhood, defined by binding. Virgo is a nearby city, large enough to affect traffic patterns but not close enough to pull us in. The scale difference also highlights why galaxy clusters are such important laboratories for studying extreme environments. Conditions in Virgo are very different from those in the local group. By comparing the two, astronomers can isolate the effects of environment on galaxy evolution. Clusters like Virgo show what happens when galaxies are packed together. Groups like ours show what happens when galaxies are relatively isolated. Both outcomes are common in the universe, and understanding both is necessary for a complete picture. Looking beyond Virgo, the pattern continues. There are other clusters, other filaments, other voids, each contributing to the grand architecture of the universe. The local group is one small piece of this structure, but it is not insignificant. Its size, mass, and relative isolation make it a valuable reference point. From a human perspective, the local group already stretches imagination. Adding Virgo and larger structures pushes that imagination further. Distances of tens and hundreds of millions of light years are difficult to conceptualize. Yet these scales are part of the same continuous system. One way to ground this is to remember that the same physical laws apply at every level. Gravity works the same way between stars as it does between galaxies and clusters. The difference lies in scale and quantity, not in principle. This continuity means that understanding the local group helps build intuition for larger structures. The overlapping dark matter halos that bind our group together are analogous to the halos that bind clusters. The filaments connecting clusters are extensions of the same dark matter web that shapes groups. In this sense, the local group is a microcosm of the universe's structure. It contains many of the same elements, just on a smaller scale. Studying it provides insight into processes that operate everywhere. The presence of Virgo also reminds us that size is relative. The local group is large compared to individual galaxies. It is small compared to clusters. Clusters are small compared to superclusters. Superclusters are small compared to the observable universe. This relativity of scale can be unsettling, but it can also be stabilizing. There is always a larger context, but there is also always a local structure where relationships matter. The local group is where gravitational relationships matter most to us. As the universe continues to evolve, the contrast between local and distant structures will become more pronounced. Expansion will carry distant clusters farther away. Virgo itself may eventually recede beyond observational reach, its light stretched and dimmed by expanding space. In that distant future, the local group may stand alone, its members bound together while everything else fades from view. The structures beyond us, so prominent now, will become inaccessible. The local group's size will then define the entire observable universe. Seen from that perspective, understanding what lies beyond us now takes on a quiet significance. Virgo and larger structures represent connections that will not last forever. They are part of a universe that is still richly interconnected, still visible, still expansive. For now, those connections shape how we move, how we measure scale, and how we understand our place. The local group is large, but it is not the end of structure. It is one level in a vast hierarchy linked by gravity to realms far beyond its own boundaries. Pulling back even farther, beyond individual clusters like Virgo, and beyond the filaments that connect them, the universe begins to reveal its largest recognizable patterns. At this scale, words like group and cluster start to feel inadequate. The structures here are vast beyond easy comprehension, spanning hundreds of millions of light years, shaped not by single gravitational centers, but by the collective pull of enormous regions of mass. It is within this context that the local group finds its place inside something much larger, known as the Lania supercluster. Lania is not a cluster in the traditional sense. It is not a tight, gravitationally bound object where all members orbit a common center in a stable way. Instead, it is a region of space defined by motion. Galaxies within Lania share a common flow, moving along similar paths under the influence of large-scale gravity. The name itself reflects this idea, meaning immense heaven, and it was chosen to capture both the scale and the unifying nature of this structure. The concept of Lania emerged from detailed studies of galaxy motions rather than just their positions. Astronomers noticed that many nearby galaxy groups and clusters, including the local group and the Virgo cluster, were moving in roughly the same general direction. These motions could not be explained solely by cosmic expansion. Something larger was shaping their trajectories. By mapping the velocities of thousands of galaxies and subtracting the effect of expansion, scientists were able to trace the flow of matter through space. What emerged was a picture of vast regions where galaxies stream toward common gravitational basins. Lania is one such basin, encompassing a volume roughly 500 million light-years across. Within this immense region lie tens of thousands of galaxies, organized into groups, clusters, and filaments. The local group sits near the outskirts of this supercluster, not at its center. Virgo, which already feels immense compared to our local neighborhood, is itself just one node within this much larger structure. Understanding Lania helps reframe the question of size once again. The local group spans a few million light-years. The Virgo cluster influences regions tens of millions of light-years across. Lania stretches hundreds of millions. Each step outward increases scale by an order of magnitude, and with it the complexity of gravitational relationships. What defines Lania is not a hard boundary. Like the local group, it does not have an edge you could draw on a map with confidence. Instead, its extent is defined by the direction of galaxy motions. Galaxies inside Lania tend to flow toward a region known as the Great Attractor, a massive concentration of matter located deep within the supercluster. The Great Attractor itself is not a single object. It is a region where mass is particularly concentrated, likely consisting of multiple clusters and large amounts of dark matter. Its gravity subtly influences the motion of galaxies across vast distances, including our own. The local group's drift through space, discussed earlier, is partly a response to this larger gravitational landscape. While Virgo exerts a strong nearby pull, Lania provides the broader context in which that pull operates. The local group's motion is shaped by a combination of influences layered across scales. Within Lania galaxies are not evenly distributed. Matter tends to collect along filaments, forming long strands that connect clusters and groups. These filaments are part of the cosmic web, the largest scale structure formed by gravity in the universe. Between them lie enormous voids, regions with relatively little matter. The local group resides near one of these filaments, connected indirectly to Virgo and other clusters. This placement affects how matter flows in our region and helps explain the local group's elongated shape and motion. Gravity does not pull uniformly from all directions. It pulls more strongly along these filaments, guiding the movement of galaxies over cosmic time. Dark matter dominates this entire structure. Just as dark matter halos define galaxies and groups, Dark matter filaments define superclusters. The luminous galaxies trace these filaments, lighting up the underlying scaffolding. Without dark matter, Lania would not exist as a coherent flow region. The scale of Lania challenges intuition. 500 million light-years is a distance so large that even light, travelling at its immense speed, would take 500 million years to cross it. Human history, all of it, occupies a barely perceptible fraction of that time. Even the age of complex life on Earth is small compared to the timescales involved. Yet despite this vastness, Lania is not permanent. On the larger scales, the expansion of the universe continues to accelerate due to dark energy. This acceleration is gradually overpowering gravity's ability to draw structures together across great distances. This means that while galaxies within Lania currently share a common flow, that flow will not last forever. Over time, expansion will stretch space faster than gravity can compensate. The supercluster will lose its coherence, its members gradually drifting apart in an accelerating universe. This realization adds an important nuance to the idea of superclusters. Unlike galaxy clusters, which are gravitationally bound and long-lived, superclusters are transient features. They represent regions where gravity has organized matter for now, but not necessarily for all time. In this sense, Lania is a snapshot. It is a pattern visible at this particular stage in cosmic history. In the far future, the concept of a supercluster may no longer apply because expansion will have isolated smaller bound structures from one another. That future isolation makes the local group's fate especially interesting. While Lania may disperse, the local group will remain bound. The Milky Way, Andromeda, and their merger remnants will continue to orbit one another, even as more distant structures recede beyond reach. Seen from that future perspective, Lania represents the last layer of structure that will eventually fade from view. Clusters like Virgo will disappear first, slipping beyond the observable horizon. Filaments will dissolve visually. Superclusters will become undetectable. Only the local group will remain. This gives present-day observations of Lania a quiet importance. We are living at a time when the universe is still richly structured on large scales, when connections between groups and clusters are still visible. That will not always be the case. Understanding Lania also deepens the sense of scale involved in the original question. How big is the local group really? The answer depends on context. Compared to individual galaxies, it is enormous. Compared to clusters, it is modest. Compared to superclusters, it is small. Yet size is not the only measure that matters. The local group is significant because it is bound. Its members share a future. Lania, by contrast, is a shared flow rather than a shared destiny. This distinction helps clarify how astronomers categorize cosmic structures. Groups and clusters are defined by binding. Superclusters are defined by motion and large-scale gravitational influence. They are real, but in a different way. The local group's place within Lania also shows how structure builds upward. Small fluctuations in the early universe grew into dark matter halos. Halos gathered galaxies. Galaxies formed groups. Groups gathered into clusters. Clusters connected into superclusters. Each level reflects the same underlying physics, repeated across scales. At every step, gravity competes with expansion. At small scales, gravity wins decisively. At large scales, expansion eventually dominates. Lania sits near the upper limit of gravity's organizational power in the present universe. This competition shapes the cosmic web. Filaments form where gravity has been able to draw matter together along preferred directions. Voids form where matter has been evacuated. Superclusters form where filaments intersect and mass accumulates. The local group's position within this web is not random. It reflects the initial conditions of the universe and the subsequent evolution of matter over billions of years. Slight variations in early density led to the large-scale patterns we see today. Mapping these patterns requires enormous datasets and careful analysis. Redshift surveys, distance measurements, and velocity maps all contribute. The identification of Lania itself was a result of combining these tools in a new way, focusing on motion rather than just position. This focus on motion mirrors how the local group itself is defined. Membership depends on velocity and binding, not just proximity. In this way, the same conceptual tools apply across scales. The idea that we live within Lania can feel disorienting. It pushes our sense of home far beyond anything we can picture directly. Yet it also offers a form of grounding. It places the local group within a larger pattern, showing that even our vast neighbourhood is part of something more extensive. At the same time, it reminds us that there is a limit to connectedness. Beyond superclusters, the universe becomes increasingly dominated by expansion. Structures no longer influence one another strongly. The cosmic web thins out. This limit is important when thinking about scale. The local group is large, but it exists within a universe that is both structured and dispersing. Its size and cohesion are meaningful precisely because they persist against expansion on these scales. Looking at Lania also reframes earlier discussions about boundaries. Just as the local group has a soft edge, so does Lania. Its influence fades gradually into neighbouring flow regions. There is no single point where one supercluster ends and another begins. This fuzziness is not a flaw. It reflects the continuous nature of gravity and mass distribution. The universe does not arrange itself into neat compartments. It forms gradients, flows, and networks. For the local group, being part of Lania means participating in these flows, at least for now. Our motion through space, our orientation relative to Virgo, and our future isolation are all tied to this larger context. As dark energy continues to accelerate expansion, the relevance of superclusters will diminish. Over trillions of years, even galaxies within Lania will lose causal contact with one another. The cosmic web will effectively unravel on large scales. What will remain are small islands of bound matter, like the local group's eventual merged galaxy. These islands will drift alone in an ever-darkening universe, their past connections preserved only in memory and theory. Seen against that distant future, the present structure of Lania is something like a fleeting phase. It is an arrangement that exists now, visible and measurable, but not permanent. This perspective adds depth to the idea of size. The local group's size is not just about how far its influence extends today. It is about how long that influence will matter. In the far future, the local group's effective size will be everything that remains accessible. Understanding Lania helps bridge the gap between the local and the cosmic. It shows how small structures fit into large ones, and how those large ones are themselves temporary. If the local group is embedded within a supercluster that will eventually disperse, how does cosmic expansion shape what remains bound and what does not? What role does expansion play in defining the ultimate limits of size and connection? At the largest scales imaginable, the universe is doing something very simple and very strange at the same time. It is expanding. Space itself is stretching, carrying galaxies away from one another, increasing the distances between everything that is not held together tightly enough by gravity. This expansion is not an explosion, and not a motion through space. It is space itself changing quietly and relentlessly. And in the midst of this vast process, the local group occupies a rare and interesting position. It is one of the regions that largely escapes this expansion. To understand what that means, it helps to begin with the nature of cosmic expansion itself. When astronomers say the universe is expanding, they do not mean that galaxies are flying outward from a central point. There is no center to the expansion. Instead, every region of space is stretching relative to every other region. From any galaxy, it looks as though distant galaxies are receding in all directions. This expansion was first discovered through observations of galaxy redshifts. Light from distant galaxies is shifted toward longer wavelengths, indicating that those galaxies are moving away from us. The farther away a galaxy is, the faster it appears to recede. This relationship is remarkably consistent, and is one of the foundational observations of modern cosmology. On very large scales, expansion dominates everything. Galaxy clusters move away from one another. Superclusters drift apart. Voids grow larger. Over billions of years, the universe becomes more diffuse, more spread out and less connected. But expansion is not the only force at work. Gravity operates at the same time, pulling matter together. Where gravity is strong enough, it can counteract expansion. This is why galaxies exist at all. If expansion were unopposed, matter would never have clumped together to form stars, galaxies, or groups. The local group is one of the regions where gravity has successfully resisted expansion. Its galaxies are not being carried away from one another by the stretching of space. Instead, they remain bound, moving in complex orbits shaped by mutual attraction. This balance between expansion and gravity depends on scale. At small scales, gravity dominates easily. At the scale of solar systems, expansion is utterly negligible. At the scale of galaxies, expansion still does not matter internally. Stars orbit galactic centers without being pulled apart by expanding space. At the scale of galaxy groups like the local group, gravity remains strong enough to overcome expansion. The combined mass of the group creates a gravitational well deep enough to hold its members together. This is why the Milky Way and Andromeda are moving toward each other instead of being carried apart. Beyond this scale, the balance begins to tip. At the scale of superclusters, gravity struggles. Structures like Lania are not fully bound. They are regions of common flow rather than permanent associations. Over time, expansion will pull them apart. The local group sits right at this threshold. It is large enough to be impressive, spanning millions of light years, but small enough to remain bound. It represents one of the largest structures in the universe that can truly escape expansion over cosmic time. This escape is not absolute. The local group does not exist outside the expanding universe. Space within it is still expanding in a technical sense. But the expansion is overwhelmed by gravity. The distances between galaxies inside the group do not grow with time in the way distances between unbound galaxies do. This distinction is subtle but important. Expansion is a property of space itself, but gravity reshapes space locally. Where mass is concentrated, space-time curves in such a way that local expansion is effectively cancelled. One way to visualize this is to imagine a stretching rubber sheet with the weights placed on it. The sheet stretches everywhere, but near the weights the stretching is distorted and suppressed. The local group is one of those weighted regions. Because of this, galaxies inside the local group do not follow the general Hubble flow, the smooth expansion of the universe. Their velocities are dominated by local gravitational interactions rather than by expansion. This is why Andromeda shows a blue shift instead of a red shift. Its motion toward us is not an exception to cosmic expansion. It is a demonstration of gravity's local dominance. The boundary where expansion begins to win over gravity is not sharp. As discussed earlier, it is marked by the zero velocity surface. Inside this region, galaxies abound. Outside it, they join the expansion. What makes the local group special is that it has already passed a crucial test. It has reached turnaround. In the past, its galaxies were moving apart under expansion. At some point, gravity slowed that expansion, stopped it, and reversed it. From then on, the group became a collapsing system rather than an expanding one. This turnaround is a defining moment in the life of any bound structure. It marks the point where gravity decisively takes control. The fact that the local group has already reached this stage tells us that it is not a temporary alignment. It is a long-lived system with a shared future. Cosmic expansion continues outside the group, however, and it is not slowing down. In fact, it is accelerating. Observations show that the expansion of the universe is speeding up over time due to a mysterious component known as dark energy. Dark energy acts like a repulsive effect on large scales, driving galaxies apart faster and faster. Its influence grows stronger as the universe expands and matter becomes more dilute. This acceleration has profound implications for structure. In the distant future, expansion will dominate more and more strongly. Even some structures that are currently marginally bound may eventually be pulled apart. The local group, however, is dense enough to resist this fate. Its internal gravity is strong compared to the effect of dark energy at these scales. While expansion will isolate the group from the rest of the universe, it will not tear the group itself apart. This means that the local group is one of the last refugees from expansion. Over trillions of years, distant galaxies will recede beyond the observable horizon. Their light will be stretched to invisibility. Clusters like Virgo will disappear from view. Eventually, only the local group will remain observable from within itself. Its galaxies, merged into a single massive system, will orbit one another in an otherwise dark universe. From that future perspective, cosmic expansion will have effectively erased the large-scale structure of the universe. Filaments, clusters, and superclusters will no longer be visible. The cosmic web will dissolve into darkness. The local group's escape from expansion is therefore both a privilege and a constraint. It allows the group to remain intact, but it also isolates it. Everything beyond will be lost to observation. This future isolation highlights the importance of size today. The local group's current size determines how much of the universe will remain accessible in the long run. Anything outside its gravitational boundary will eventually slip away. Understanding this adds weight to the question of how big the local group really is. Its size is not just a matter of spatial extent, it is a matter of destiny. The larger the bound region, the more matter and structure will remain connected in the far future. The local group is large enough to include several major galaxies and dozens of dwarfs. It is not large enough to include clusters like Virgo. Those will be lost. In that sense, the local group defines the limits of permanence in an accelerating universe. It is the largest structure we are part of that will remain gravitationally intact indefinitely. This perspective also reframes earlier discussions about boundaries. The local group's boundary is not just where gravity fades today, it is where permanence ends. Beyond that boundary, nothing remains bound to us over the longest timescales. Cosmic expansion is not something the local group avoids completely. It shapes the environment around it. It determines what lies beyond reach. But internally, the group lives in a different regime, one where gravity writes the rules. This duality is one of the most striking features of the universe. Expansion dominates the big picture, gravity dominates the local one. The local group sits at the intersection of these two behaviours. From a human point of view, this is almost impossible to feel. The expansion of the universe does not affect daily life. Gravity feels constant and immediate, yet on cosmic scales, these forces decide the ultimate structure of reality. The local group's escape from expansion is not dramatic. There is no barrier, no shockwave, no visible transition. It is simply the result of mass and distance falling on one side of a balance rather than the other. This quiet balance is what allows galaxies to have long, complex histories. It allows stars to orbit, planets to form, and life to arise without being torn apart by cosmic stretching. In that sense, the local group size is intimately connected to our existence. A smaller group might not have resisted expansion as effectively. A denser environment might have been too violent. The local group occupies a narrow window where stability is possible. As expansion continues to accelerate, this window will become rarer. Bound structures will become isolated islands in an ever larger sea of empty space. The local group will be one of those islands. Thinking about this can shift how we view scale. Size is not just about how far something extends, it is about how long it holds together. The local group is large enough to endure. If cosmic expansion will eventually strip away everything beyond the local group, what would our neighbourhood look like if we could step outside it entirely and see it from afar? Try, for a moment, to imagine a viewpoint that no one could ever actually reach. Not just far from Earth, not just outside the Milky Way, but far enough away that the entire local group comes into view at once. From that impossible distance, the familiar sense of scale dissolves. Galaxies that once felt enormous become small shapes. Distances that once felt endless compress into patterns. And the local group, which from the inside feels like an immense and loosely defined region, begins to reveal its overall form. From the outside, the local group would not look crowded. It would not resemble the dense, glittering clusters often shown in astronomical illustrations. Instead, it would appear sparse, irregular, and quietly spread out. A handful of brighter concentrations would stand out, surrounded by darkness that dominates the scene. The most obvious features would be the Milky Way and Andromeda. Even from millions of light years away, they would still be the brightest and most massive structures in the group. Their spiral shapes might be visible as faint disks, their central bulges glowing more strongly than their outer arms. Around each, a diffuse halo of stars would extend outward, blending gradually into the surrounding dark. Between them, the space would not be empty in the strict sense, but it would be mostly dark. Thin gas, scattered stars, and vast amounts of dark matter would fill the region, but none of it would shine brightly. The separation between the two galaxies would be the dominant feature, a gulf spanning millions of light years that gravity quietly bridges. Triangulum would appear nearby, smaller and less imposing, but clearly part of the same system. Its spiral structure would be visible only faintly, its disk thinner and less luminous. From this external vantage point, its subordinate role would be obvious, yet its presence would still add weight and complexity to the overall arrangement. The dwarf galaxies would be far harder to see. Most would not stand out at all unless you knew exactly where to look. They would appear as tiny dim smudges, scattered unevenly around the larger galaxies. Some would cluster near the Milky Way, others would cluster near Andromeda. A few would drift in the space between, marking the local group's extended reach. If you could see dark matter, the picture would change dramatically. The local group would no longer look like a sparse collection of islands. Instead, it would appear as a broad, overlapping structure with massive halos surrounding each major galaxy and merging into one another. These halos would define the group far more clearly than the visible stars ever could. From the outside, the local group's true size would be set not by where the light fades, but by where the dark matter density drops low enough that gravity no longer binds galaxies together, stretched, elongated along the axis connecting the Milky Way and Andromeda. This elongation reflects the group's formation history and the way matter has flowed into this region over billions of years. If you could watch the local group over time from this distant perspective, motion would be subtle but meaningful. The Milky Way and Andromeda would drift closer together, almost imperceptibly at first. Over millions of years, the change would become noticeable. Over billions, undeniable. The dwarf galaxies would trace slow arcs through space. Some would spiral inward, others would be nudged outward. A few would be torn apart, their stars stretched into long streams that would blend into the halos of the larger galaxies. From afar, these streams might appear as faint wisps, evidence of past interactions written across space. What would be striking from this outside view is how empty the local group really is. The galaxies would occupy only a tiny fraction of the total volume. Most of the space would be darkness, not because nothing exists there, but because what exists does not emit light. This emptiness is easy to underestimate from the inside. When looking up at the night sky, stars feel abundant. Constellations fill the dome above. But those stars are confined to a thin disk within a single galaxy. From outside, the Milky Way stars would be tightly packed into a relatively small region, surrounded by vast expanses of nearly empty space. The local group would also appear isolated. Beyond its boundary, other galaxies and groups would lie far away, separated by distances much larger than the separations within the group itself. The nearest large cluster, Virgo, would appear as a distant concentration, well outside the local group's gravitational reach. From this vantage point, the local group would look like a modest association, neither tiny nor overwhelming. It would not dominate the universe, It would be one node among many in the cosmic web. Yet it would also be clearly defined, its members sharing a common gravitational fate. If you could step even farther back, the local group would begin to blend into the larger structures around it. Filaments of galaxies would become visible, connecting groups and clusters. The local group would appear as part of a larger flow of matter, drawn toward regions of greater mass. At that scale, individual galaxies would lose their identity, becoming points of light within a much larger pattern. The local group would still exist as a concept, but it would be one detail among many. This outside view helps clarify something important about size. From within the local group, distances feel enormous. 2.5 million light-years between the Milky Way and Andromeda feels almost inconceivable. From far outside, that distance becomes just one feature in a broader arrangement. Scale is always relative to perspective. What feels vast from one position can feel modest from another. The local group is large relative to a single galaxy. It is small relative to a supercluster. Both statements are true at the same time. Seeing the local group from outside would also reveal how temporary its current appearance is. The separation between the Milky Way and Andromeda would not look permanent. Their approach would be evident, their future merger implied by their motion and overlapping halos. The group's shape would slowly evolve. Over billions of years, the two largest galaxies would merge, reducing the number of major light sources. The local group would become more compact, its internal distances shrinking, even as its mass remained similar. From the outside, this evolution would look like consolidation. A loose arrangement would gradually tighten. A handful of bright centers would become one. The surrounding dwarf galaxies would be absorbed or scattered, their individual identities lost. In the very distant future, an outside observer would see the local group as a single massive galaxy, surrounded by a sparse halo of remnants. The structure would still exist, but it would be simpler, less varied. This imagined outside perspective also highlights how the local group fits into cosmic time. The arrangement we see now is not the beginning or the end. It is a middle stage shaped by past expansion and future merger. From this view, the local group's escape from cosmic expansion becomes clearer. While everything around it drifts away, the group holds together. Its boundary marks the limit of that cohesion. The space just beyond the local group would show galaxies receding, their separation increasing over time. From outside, the contrast between bound and unbound regions would be subtle but measurable in motion. Over trillions of years, that contrast would sharpen. The local group would become increasingly isolated. Distant structures would fade from view as expansion accelerates. From an external vantage point far in the future, the local group might appear as one of many isolated islands, each drifting alone in an ever-expanding universe. From inside, this future is abstract. From outside, it would be obvious. The local group's size would define the limits of connection. There is also something humbling about imagining this view. Every human story, every planet, every living thing that has ever existed occupies a tiny, nearly invisible part of one galaxy in this loose group. From outside, Earth would not be a point of light. It would be completely invisible. And yet, the fact that we can imagine this perspective at all is remarkable. The local group is large enough to require concepts like light years and dark matter to describe it, but structured enough to be understood. Seeing it from outside would strip away emotional attachment and replace it with pattern. It would show relationships rather than locations, motion rather than landmarks. From that vantage point, the local group would not feel like home. It would feel like a system, a collection of mass responding to gravity over immense distances. And still, even from that distance, one could trace a path inward. From the supercluster, to the filament, to the group, to the galaxy, to the star, to the planet, each level nested within the next. This nesting is what gives scale meaning. The local group matters not because it is the largest structure, but because it is the largest one we meaningfully belong to. Imagining it from outside also clarifies why its size is so often misunderstood. We tend to focus on visible matter. From outside, it would be obvious that most of the structure is invisible. Dark matter would dominate the scene. The visible galaxies would look like decorations on a much larger framework. Without that framework, the arrangement would not exist. From far away, the local group would also look quiet. There would be no explosions, no sudden changes, no dramatic flares. Everything would move slowly. Even the merger of galaxies would take place over timescales so long that it would feel almost static. This quietness is deceptive. Over time it leads to profound transformation. Slow processes accumulate. Small motions add up. The local group's future is shaped not by sudden events, but by steady gravitational influence. Seeing it from outside would make that clear. The local group is not dramatic because it does not need to be. Gravity does its work patiently. This imagined view also reinforces why the local group is a useful concept. It is a scale at which the universe becomes manageable, large enough to be impressive, small enough to be coherent. From outside, it would be easy to identify as a single entity. From inside, its boundaries feel ambiguous. Both perspectives are valid. As we draw closer to the end of this exploration, that duality becomes important. The local group is vast, but it is also intimate. It is enormous, but it is also the smallest meaningful cosmic neighborhood we can call our own. Seeing it from outside helps gather all these ideas into a single image. A loose collection of galaxies bound by invisible mass, drifting through an expanding universe, slowly evolving toward a quieter, more compact future. After tracing size, motion, boundaries, and future, one question remains. What does it mean, practically and philosophically, to belong to something this large? By the time we arrive here, the local group no longer feels like an abstract term. It has shape now, even if that shape is soft. It has motion, history, and a future that stretches far beyond human timescales. What began as a simple question about size has unfolded into something broader and quieter. Not just how big the local group is, but what kind of place it is, and what it means to exist within it. The local group is vast in a way that resists drama. It does not overwhelm through spectacle. It does not announce itself with bright edges or sharp borders. Instead, it reveals itself slowly, through relationships, through gravity, through motion measured over millions and billions of years. Its scale is not something you grasp all at once. It settles in gradually, the way distance does when you truly stop to think about it. From inside, the local group feels almost empty. Space dominates. The Milky Way feels immense, and everything beyond it feels remote. And yet, step back far enough, even in imagination, and the local group becomes a single, coherent thing. A loose island of matter, held together not by proximity but by shared fate. This idea of a shared fate may be the most important part. The Milky Way, Andromeda, triangulum, and dozens of smaller galaxies are not simply near one another by chance. They are bound, their motions are linked. What happens to one eventually influences the others. Over time, they will merge, reshape, and consolidate. The local group is not just a region of space. It is a long story unfolding. Size, in this context, becomes more than distance. It becomes duration. The local group is large enough to endure, large enough to resist cosmic expansion, large enough to remain intact while much of the universe drifts away. That endurance gives it a quiet significance. In the far future, when expansion has carried distant galaxies beyond visibility, when clusters and superclusters have slipped out of reach, the local group will remain. Its internal gravity will continue to hold it together. Its stars will continue to orbit. Its merged remnants will still glow, even as the broader universe grows dark. From that distant future, the local group will not seem small at all. It will be everything that remains accessible. All other structures will be theoretical, inferred, remembered but not observed. The local group will define the observable universe for whatever observers exist then. That future perspective casts the present in a different light. Right now, we live in a universe where structure is layered and abundant. Groups connect to clusters. Clusters connect to filaments. Superclusters trace patterns across hundreds of millions of light years. We can still see outward, still place ourselves within a vast network. But even now, the local group already marks a boundary of belonging. Everything inside it is gravitationally connected to us. Everything outside it is not. That distinction will only grow sharper with time. It is also worth noticing how calm the local group is. Compared to dense clusters, where galaxies rush past one another at thousands of kilometers per second, our neighborhood is gentle. Interactions happen slowly. Mergers take billions of years. Change unfolds at a pace that allows structure to persist. This calmness is not incidental. It is part of why the Milky Way looks the way it does. It is part of why stars have formed steadily for billions of years. It is part of why planetary systems can remain stable over long spans of time. In a denser environment, that stability would be harder to maintain. Close encounters could disrupt orbits. Gas could be stripped away. Star formation could be quenched or triggered too violently. The local group occupies a kind of middle ground, large enough to be stable, sparse enough to be gentle. That balance is easy to overlook when thinking only in terms of size. But scale is not just about how far something extends, it is about how conditions change across that extent. The local group's scale supports continuity rather than chaos. There is also something quietly grounding about realizing that the local group is not centered on us. The Milky Way is important within it, but not dominant. Andromeda matches and slightly exceeds it in mass. The center of gravity lies between them, not within our galaxy. This lack of centrality is not disorienting, it is clarifying. It places us within a system rather than at its focus. It reminds us that belonging does not require centrality. It requires connection. The local group is defined by those connections, the overlapping dark matter halos, the shared gravitational basin, the collective motion through space. These are not things we see directly, but they are the framework within which everything else happens. When we talk about the size of the local group then, we are really talking about the reach of influence, how far gravity extends, how much matter is involved, how long the structure will persist. All of these are aspects of size that go beyond simple distance. In everyday life, size is easy to judge. A room has walls, a city has borders, a country has boundaries. In the universe, size is rarely that clean. It fades rather than ends. It is defined by thresholds rather than edges. The local group exemplifies this. Its boundary is where gravity loses its grip, where expansion takes over, where shared future gives way to separation. That boundary is not visible, but it is meaningful. Understanding that helps bring together everything explored so far: the galaxies, the distances, the dark matter, the motion, the future merger, the escape from expansion. All of these pieces fit into a single picture. That picture is not one of isolation. Even as the local group is an island, it is not alone in the present universe. It is part of a larger web, connected for now to clusters and superclusters through gravitational influence and shared motion. But it is also an island in the deeper sense. It is a region where gravity has carved out a long-lasting pocket of connection within an expanding cosmos. That is what makes it special. From a human point of view, this scale is difficult to internalize. Millions of light years do not translate easily into lived experience. Neither do billions of years. But the local group offers a way to anchor those abstractions. It is not the entire universe. It is not even a large fraction of it. But it is the largest structure we meaningfully belong to. Everything closer than it is nested within it. Everything farther than it will eventually drift away. There is something quietly reassuring in that. No matter how vast the universe becomes, there is a finite region that remains connected. A region where gravity still matters. A region where structure persists. The local group is not static, but it is patient. Its changes are slow. Its future is long. It gives a sense of continuity that stands in contrast to the rapid pace of human life. Thinking about it can slow the mind. Distances stretch. Time expands. Urgency fades. The local group does not hurry, and nothing within it needs to. Even the eventual merger of galaxies, which sounds dramatic when stated plainly, unfolds with enormous restraint. No sudden endings, no sharp conclusions, just gradual transformation. That same quality applies to understanding. There is no single moment where the size of the local group becomes obvious. It emerges as you layer idea upon idea, distance upon distance, time upon time. In that sense, asking how big the local group is leads naturally to asking how we measure bigness at all. Is it distance, mass, duration, influence? The answer depends on what you value. Astronomers tend to value gravitational binding and motion. By that measure, the local group is large enough to matter in the deepest sense. It holds together, it resists dispersal, it has a future. From a quieter perspective, one less concerned with definitions, the local group can simply be thought of as home territory on the largest meaningful scale. Not home in a sentimental way, but in a structural one. It is the region of the universe where events are connected, where motions are related, where gravity ensures that what happens in one place eventually affects another. That connection does not make the local group small, it makes it coherent, and coherence is what allows understanding. A structure too small tells us little about the universe. A structure too large dissolves into abstraction. The local group sits in between. It is large enough to contain complexity, small enough to be studied in detail, long-lived enough to have a meaningful history and future. That combination is rare. As you sit here now, wherever you are, the local group continues its slow drift through space. Galaxies move imperceptibly. Dark matter shapes trajectories without light or sound. Expansion pulls outward beyond the group's edge. Nothing about this requires attention. It will continue whether or not anyone observes it. That independence is part of what makes it calming. There is no obligation to understand it all at once. No need to hold every number in mind. The local group does not demand comprehension. It simply exists, and within it, so do we. This shared island of galaxies is vast, but it is not infinite. It is structured, but not rigid. It is dynamic, but not chaotic. It is immense, but not overwhelming once you allow yourself to settle into its scale. If there is any comfort to take from this perspective, it is that even in an expanding universe, not everything is drifting apart. Some things remain together, some connections endure. The local group is one of those enduring connections, quiet, patient and immense in a way that does not need to impress. You do not need to resolve it. You do not need to picture every galaxy or every light year. It is enough to know that there is a place, far larger than anything familiar, where gravity has drawn matter into a shared path, a place where time moves slowly, where change is gradual, where structure persists. That place is not distant in the way other cosmic structures are distant. It includes us by default. It includes everything we have talked about and everything we will ever directly know. The local group is not the universe, but it is our part of it. And for something measured in millions of light years and billions of years, that is a surprisingly gentle thought to rest with.